Sorry I'm late. My laptop audio wasn't working. Um Maybe we should wait a few more minutes anyways, in case people are still joining. Okay, let's wait a little bit. Let me share my screen and make sure that's working. Give me a sec. Let me pull up the notes. In the meanwhile, does anyone have questions on content from that we covered before? Because it's today's stuff is gonna build up on that a lot. Yeah. Okay, let me share my screen. Mm. Can you guys see that? Like just a thumbs up or something like that. I think if you can't see, then tell me. Um, okay. Actually, one thing I wanted to do first before was like in terms of just like an overview of the placement, right? So here are the topics. Okay. Um, Normally past final exams have been 9 questions. So I'm going to assume that the placement test will be somewhat like 9 free response questions. Because that's the best guess you can take, considering that's how the finals usually go. Um, let's see how the breakdown will look like, right? The thing is, this whole like up until here is what we talked about last time. There'll probably be like 3 to 4 questions from here, and then 4 to 5 questions will be the second part of the course. So let's like do a quick split up. So you'll definitely have 1 question on linear transformations. So for sure. 1 to 2 questions on like diagonalization with the way we did last time, with like eigenvectors and eigenvalues and eigenvectors, and then Jordan canonical form. That's guaranteed 1 to 2 questions there. Um, then out of the differential equations, you'll have like 1 normal and then 1 system. So that's 2 more questions there. So that's 5 questions. And then you'll have probably like, you know, 2 to 3 questions from here. And that should be the split up, something like that. So the second half of the course is quite important because there's going to be a lot of questions, potentially a lot of questions on differential equations and stuff like that. So we'll go over that today. Okay, so let's now start the material for today. Um, one last time, like diagonalization should make sense what we did last time because we're literally going to build off of that. We're going to build off of that right now. So that's the solutions. We want these. Okay. Let's see. Um, all right. So here are the table of contents for today. It's only 4 chapters, but these are like the bulkiest chapters of all time. They're pretty like content heavy. So let's get started. So remember last time we talked about matrices being diagonalizable, and all that means is that you can take any matrix A, right, a square matrix A, and write it as PDP inverse, where P is a matrix with all of the eigenvectors stacked as columns. So I'll write it like that, right? So V3, etc., right? And D is a matrix with all of the eigenvalues along the diagonal. Okay. Um, we talked about all this last time. Now, this happens, we're only allowed to do this in a specific case, and that's when the algebraic multiplicity of each eigenvalue equals its geometric multiplicity. So let's review what that means. So if we have when we go to find eigenvalues, right, we do determinant of a minus lambda I equals 0. And that gives us some equation like maybe lambda minus 2 squared times lambda minus 3 equals 0. So this tells us we have 2 eigenvalues here, lambda equals 2 and lambda equals 3, but lambda equals 2 has an algebraic multiplicity of 2 because of this power of 2, and lambda equals 3 has an algebraic multiplicity of 1. Okay, so that's algebraic multiplicity. Geometric multiplicity means, okay, now when we do a minus lambda I times v equals 0 to find each eigenvector, the kernel of this a minus lambda I, as in the number of vectors in the solution that we get for v, is the geometric multiplicity. So let's say we solve a minus lambda I times v equals 0 for lambda equals 2. So we do a minus 2I times v equals 0. Okay, and we get that the solution set of v is the vectors like is 1 0. Okay, so 1 0 is the kernel of a minus 2I. Remember, kernel just means the solution set to a matrix times a vector equals 0. So v is the kernel. Um, as you can see, the kernel is one-dimensional. We have one vector in the kernel, so this would be a geometric multiplicity of 1. So as you can see, for lambda equals 2, the algebraic multiplicity is 2, the geometric multiplicity is 1. That means that this matrix right here, A, would not be diagonalizable. So A would not be able to be written as PD, P inverse. We want to get as close as we can to this diagonalization. So this is where we introduce the Jordan canonical form. Basically, all it is instead of, we can't get A equals P dP inverse, so we settle for like the next best option. And instead, we're going to write A as P JP inverse. So instead of having a nice clean diagonal matrix, right? Remember our diagonal matrix looks like this. Instead of having that, we're going to have some J matrix, which is going to closely, mimic this, but it's not going to be the exact same. So let's see what that looks like. That's kind of the context. That's like why we're doing all of this. Okay. So you only have to deal with Jordan canonical form when your algebraic multiplicities and geometric multiplicities are not equal. Okay. So let's first think about what our J matrix looks like. This is a bit confusing at first, but once you get it, it definitely will click. So our D matrix, nice diagonal matrix, easy to understand, right? It just has numbers along the diagonal, those are the eigenvalues, and zeros everywhere else. Jordan blocks, so a Jordan matrix J is composed of a bunch of Jordan blocks inside of it, okay? So each one of these little things could be a Jordan block, and you'll see what I mean. Let's look at what a Jordan block means. Let's look at the first type of Jordan block. If it's 1 by 1, that's a 1 by 1 matrix. There's only one option, right? That's kind of doesn't make any sense. If it's 2 by 2, right? A 2 by 2 diagonal matrix would look like lambda, lambda, 0, 0. But, so this is D, but J looks like lambda, lambda, and in the top right we have a 1. So we call this the super diagonal. Here is our diagonal across the matrix, right? The super diagonal is the diagonal to the top right of that diagonal. So it's more evident in the 3 by 3 case. Look at the 3 by 3 case, right? A regular D matrix would look like lambda, 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 0, 0, 0, 0, 0, 0, right? But a Jordan block, a 3 by 3 Jordan block, is going to have those lambdas across the diagonal, but additionally, ones along the super diagonal and zeros everywhere else. So this is what we mean by we're getting as close as we can to D matrix without actually, because we can't actually get D because our matrix isn't diagonalizable. Okay, 4 by 4, same idea. Lambdas all across the main diagonal and ones across the super diagonal, zeros everywhere else. Okay, now all a big J matrix is it's a combination of all of these, of a bunch of these smaller Jordan block matrices along the diagonal. Let's look at an example. So I think we'll have examples here. So check this one out, right? This matrix J right here, the first one, let's see, we have, here's a Jordan block there in pink. So that's our 2 by 2 Jordan block, right? With an eigenvalue lambda 1. And then our next Jordan block is just a 1 by 1 Jordan block. So that's why I put the 1 by 1 Jordan block, because that's just like a number. If you just see a number there, that's a 1 by 1 Jordan block, right? So this one is lambda 2, and then this one would be lambda 1. Okay? Let's look at another example, right? So we go down. If we look at this example, right? Here, our first Jordan block is a 1 by 1 Jordan block. Then our next one looks to be a 2 by 2 Jordan block, correct? And our final one, then it looks like we get another 2 by 2 Jordan block and a 1 by 1 Jordan block, okay? The first thing is the eigenvalues here are very clear, right? Like we split it up into lambda 1, lambda 2s, lambda 3s, lambda 4s. That's one way to see it. But there's also a case where you have repeated eigenvalues, so that's not the only way to see it. The reason I know, for example, that this is not one big 3 by 3 Jordan block is because, look, if it was a 3 by 3 Jordan block, then we should have numbers across the diagonal and ones always across the whole super diagonal, but here we don't have a 1. So this could not be a 3 by 3 Jordan block, and that tells me that, okay, it has to be split into a 2 by 2 and a 1 by 1. Okay, last one. It's good to be able to see this pattern. Try and think through this one as well on your own, right? This one's pretty simple. A 3 by 3 block and then a 2 by 2 block. Okay. So once like you should be comfortable with like if I say okay, because the way it's going to work is when you're trying to find J, you're going to think about it in terms of blocks. You're going to be like, oh, I have a 3 by 3 block and then a 4 by 4 block. So you should be able to, okay, let's make this matrix, right? So it's going to be a 7 by 7 matrix. I know the diagonal is going to have all my eigenvalues. Let's say this one is for lambda 1 and this one is for lambda 2. So lambda 1, lambda 1, lambda 1, three of them, and then 4 for lambda 2. And then I'm going to have this. Let's first isolate this 3 by 3 Jordan block first. So it's going to have ones along the super diagonal and 0 everywhere else, right? Then look at my 4 by 4 Jordan block here. Ones along the super diagonal. So 1, 1, 1, 1. I know it's a little bit messy. Zeros everywhere else. And this whole thing, if you're doing an exam, don't write all the zeros. You just put a big 0 to show like it's zeros everywhere else. Okay? So as you can see, it's not because this matrix doesn't have this whole matrix J doesn't have ones across the whole super diagonal, right? There's a gap here where here there's going to be a 0, right? Above this lambda 2 and to the right of this lambda 1. So don't get fooled and just say, oh, I have a 7 by 7 Jordan matrix. I can just do lambdas across the whole diagonal and ones across the super diagonal. No, you have to think about it in terms of the blocks that make it up. Okay. All right. So now how do we actually find like P and J and whatnot? Okay. So there's two types of scenarios where you'll have to where you're gonna be dealing with Jordan form. The first one, the first problem, they'll give you a bunch of information about J. So here's an example problem of that. Like something like what is it? Down here. Like it'll say, okay, let A be a 7 by 7 matrix, find the Jordan form J, and they give a bunch of random information. We'll deal with that second case later. Let's first solve the first type of problem, which is like we're given a matrix A and we have to find P and J. So pretty much what we did before with diagonalization, but now instead of D, we have J. Okay? So what we do, let's say we're given this problem. Find the Jordan canonical form and the transformation matrix P. So find P and J such that A equals PJP inverse given this matrix A. Okay. Now, the thing is, they don't even have to tell you like that you need to do Jordan canonical form. You should be able to figure it out. Why? Because we're going to diagonalize this and we're going to see that algebraic multiplicity is not going to equal geometric multiplicity. And that's why we're going to need Jordan canonical form in the first place. Okay. So you should be able to spot when you need to use Jordan canonical form and when you don't. Okay, so step one is just like normal. We need to find eigenvalues. So we solve determinant A minus lambda I equals 0. And we get this guy for our characteristic polynomial. Okay, then we go down, we factor it, and we see that this is our equation, and we solve lambda equals 3 with algebraic multiplicity of 2. So this is my first indicator that, this is a little bit suspicious that lambda equals 3 has an algebraic multiplicity of 2. Right? That means that if we want to be able to diagonalize this as A equals PDP inverse, then the geometric multiplicity must also be 2. If it's not, then we have to do PJP inverse. So let's see which case we're in. So we find the geometric multiplicity, as in we solve for the nullity of A minus lambda I. So lambda is 3. And because lambda is 3, we do A minus 3I. We get this matrix. Let's find the nullity. Hopefully this should be like second nature by now. We row reduce and we get this matrix. And then the nullity, right? We're looking for this matrix times an x1, x2 equals 0. Right? And then you can really choose any x1 and x2 that work. A clear answer here is x1 is positive 1 and then x2 is negative 2. Right? Because I'll make 1 minus 1 equals 0. But you can also solve it out using the way we're used to seeing. Okay, but anyways, we get that our basis vector for the null space is 1, -2. And that's the only one, right? There's no other vectors in the null space that form like a new basis. Obviously, 1, -2 is 1, and 2, -4 is 1, because these are just multiples of each other, but those don't count, right? Those are not linearly independent. Those are linearly dependent. So because our null space is 1, -2, we know the dimension of the null space, right? Dimension of the null space, which is equal to the nullity. That's the definition of the nullity equals 1. So there's an issue, right? Geometric multiplicity is 1, algebraic multiplicity was 2. So basically, the reason why this is an issue is because if the algebraic multiplicity is 2, that means that we should be getting 2 eigenvalues, eigenvectors for this eigenvalue. That should be the case. However, we're not. Here, we're only getting 1 eigenvector. So that's why we have an issue in the first place. So it looks like we're going to need Jordan canonical form. So let's see how we deal with that. Now, the thing is, right, we have 1 eigenvector. We need a second one, right? We weren't lucky enough to be given 2 here. So that's why we're needing to use Jordan form. How do we find the second one? We use these things called generalized eigenvectors. Okay, so what that means is before, to find our eigenvectors, we were doing a minus lambda I, so 3i times vector equals 0, eigenvector equals 0. Now we need to square this a minus 3i matrix, okay, to find the generalized eigenvector. So we're going to do a minus lambda I, so 3i squared, and we're going to solve this to find the new eigenvector. Okay. And you're going to see it's going to form like a chain of eigenvectors. So let's do that, right? We find a minus lambda I squared. So that's just taking a minus 3i and multiplying it by itself. And we get out the matrix 0, 0, and 0, 0. So basically now we're solving, right? This matrix becomes 0, 0, 0, 0 times v equals 0. So clearly then like a null space for this could be sorry, not v. Yeah, v could equal any multiple of 1, 0 or 0, 1. Right? Because any one of those those are, first of all, those are linearly independent, and any one of those will make this equation true. So here we can see now we have 2 eigenvectors. But now the question is, okay, we have 2 eigenvectors here, which is what we wanted, but what do we do with our old eigenvector and blah, blah, blah? So this is where we think about the chain. So where do we show the chain? Yeah, so here's what the chain should look like. It should say, okay, your first vector, your first eigenvector, okay, should equal a minus 3i times your second eigenvector, which is the one that we just found. Okay, if you have more, right, you're going to continue this chain down. Basically, basically what we do is, okay, so let's make it clear. So we found the kernel of a minus 3i, right? And that was -1, 2, or 1, -2. What was it? Let me check. I think it was, yeah, 1, -2. Okay. So the kernel of a minus 3i was 1, -2, right? Now we need to find the kernel. Now we find the kernel of a minus 3i squared. And we said, okay, this is 1, 0 and 0, 1. Okay. Now we need to choose a vector from here that is linearly independent from this vector here. Okay. So either one of these would work. Let's see which one we choose in the example. Let's choose v2 equals 0, 1. So here in our example, we choose v2 equals 0, 1. So we choose our vector v2 from these vectors here, and we say, okay, let's let v2 equals this guy right here. Okay. Then we solve our chain. So v1 equals a minus lambda I times v2. In the same way, if you had higher, if you had to go, for example, to like a minus 3i cubed, then you would say, okay, v2 equals a minus 3i times v3. So you would given v3, you'd choose v3, then you go down and find v2, and then you go down and find v1. So it's like a chain that goes down. Okay, and I'll show a diagram to make this clear in a sec. Okay. But anyways, so we found v2, we chose v2. Now, how do we find v1? We do a minus 3i, so times v2. So a minus 3i is this guy. We multiply it by v2, and we get -1, 2. So notice how that's a little bit different than the one. Oh, is that the same? Oh, yeah, I might have. What did I write wrong here? It was, yeah, 1, -2. Sorry, I forgot to erase this negative. So notice how before we had 1, -2 as our choice, right? And now, when we do the chain thing and multiply down, we get -1, 2. So they're not always going to be the same, and that's important to realize. Okay? So now we have V1 and V2, right? Remember, just to recap, right? V1 is right here. V2 we just chose from our set here. So V2 is equal to 0, 1. And then V1 depends on V2 now. We can't just take the original V1 that we had. So we take V1 to be -1, 2. And then the way we form our P matrix is we stack V1s and V2s the same way as we used to, except here the order matters. You have to put V1 first and then V2. And then V, if you have more, you put all the way up to your nth one. So what is our P going to look like? We're going to put V1, our first eigenvector, and then our second eigenvector. And that's our P matrix. Okay? That's our P matrix right there. Okay? Let's draw a diagram to help out with this. This is what this dot diagram is here. Okay? So let's actually draw it on the side so we can draw it from scratch. So what you should do, like on a test, you should say, okay, my characteristic polynomial was lambda minus 3 squared equals 0. So basically that says I have lambda equals 3 with algebraic multiplicity of 2. Okay, so your one eigenvalue that you're dealing with is lambda equals 3. So that's your title of this diagram. Okay, then you draw a few rows. Okay, let's do 3 rows. Usually you won't need more than 3. Okay, the first row is for a minus 3i, just your basic a minus lambda I. The second row represents a minus lambda I squared. So remember, that's what we had to do when we didn't have enough eigenvectors here. We had to push up to the next level. So that's why we square. We're going up to the next next row on this dot diagram. And then potentially this one is a minus 3i cubed if we even need it. But we'll see. Okay. So what we do first is you're probably asking, okay, why is this called a dot diagram? The reason why is because each dot represents a vector in the null space. So for a minus 3i, we found that the kernel of a minus 3i was this, right? That means the nullity was 1, right? Null space of 1 vector in the kernel. So we go here and we put 1 dot on it. Okay, that's it. Then we say, okay, that wasn't enough. We need 2. So we need to go to a minus 3i squared. How many did we find for a minus 3i squared? We found 2. However, we don't put 2 new ones on the row. We say we found 1 new one, and then the other second one is already contained underneath. So like the number that you get has to continuously add up, if that makes sense. So it's like a minus 3i, right, squared, yes, has 2 vectors in the null space. One of them is new because we only had 1 before, but one of them comes from the one before, in a sense. Right, so it would be a mistake to draw the diagram like this. The other thing with the dot diagram is you can never have like a dot freestanding. If you think about like this is like a base, this is the ground, and these are towers being built up, you have to build up an actual tower. So the only way I could put a dot here is if I also had a dot here from before. Okay, so you can never like have a floating dot. If you have a floating dot, that means you know you did it wrong. Okay, so we did that, and then we were done, right? Because then we got 2 vectors, right? And we got 2 vectors in our null space, and also, right, our P matrix should be 2-dimensional, 2 by 2. So we know we're done here. Then the question is, okay, here we chose our eigenvector, right? Remember here, our kernel for a minus 3i squared, we had 2 options. We chose 0, 1. Okay. Now, how do we find the eigenvector for this one? We take 0, 1, and every time we go down a row, we multiply by a minus lambda I. So we multiply by a minus 3i. So we do a minus 3i times 0, 1, and we get this new vector here, which was what? -1, 2 for us. Okay. Then when we stack it in the P matrix, we go up. So we put this vector first, as in V1 first, -1, 2, and then V2 next, 0, 1. Okay, that's probably very confusing. You just have to do examples until it clicks, and then just do it enough times so it becomes second nature. That's finding P. Now, how do we find J? There's 2 ways of finding J. I'm going to first show you the easy way. When we did PDP inverse, right? There's also 2 ways. Let's go back to when we did A equals PDP inverse, right? When you found P, okay, you could find D by like doing, because you know A, you know P, So you could multiply by P inverse here and then P here, right? And then these would cancel and these would cancel, and you would get P inverse AP equals D. So you could solve for D like that, but also you could just say, okay, I know D is a diagonal matrix with the eigenvalues, and I know what the eigenvalues are. So why don't I just say that like D is a diagonal matrix? I know my eigenvalues, so I put them on the diagonal, and then it zeros everywhere else, right? And if you want to check your work, you can go back and do the whole matrix multiplication up. We can do the same thing here. We can say, okay, I know J is going to have the form of like a bunch of Jordan blocks, but I just need to know what are those Jordan blocks. And that's the nice thing about this dot diagram, is that you basically just circle all your towers. So I say, okay, let's clear this up a little bit. Just draw a circle around all of your towers. So here's one tower. Here we only have one tower, right? And because we have one tower that's 2 by 2, that means this represents a 2 by 2 Jordan block. It's as simple as that. Let's take just one more example, right? Imagine our dot diagram looked like this for whatever reason. If our dot diagram looked like this, then that would mean our J matrix would be a 3 by 3 block, followed by a 2 by 2 block, followed by a 2 by 2 block. Okay, but in our case, we just have a simple 2 by 2 block. So we know what the eigenvalues are. Those are 3, and algebraic multiplicity of 2 means it comes up twice. So we put 3 here and 3 here. And it's a 2 by 2 Jordan block, so we're not going to put 0 up here. We're going to put a 1 here, and we're going to put a 0 down here. And then we're done. We've solved for P, and we solved for J. Okay, we could have, again, also have gotten J by doing, okay, we know that A equals PJ P inverse. So multiply on the left and right sides by P and then P inverse. So P and P inverse, we would get P inverse AP. These two are going to cancel. These two are going to cancel equals J. You could have also done it like that. And that's how you can verify that that should work for this case. Okay. Any questions about that process? That's for a 2 by 2. I'll leave it up if anyone wants to write anything else. They'll only ever ask you to do that either for a 2 by 2 matrix or for a 3 by 3 matrix. Other than that, you can see it just gets computationally super annoying. When they're dealing with higher dimensional matrices, that's when we're going to see the second type of problem, which we'll go to next. Any questions about this? Could we have chosen as no? So yeah, exactly. So you would have chosen V2 as 1, 0. You would not have gotten the exact same answer. You would have gotten a different P. J would have been the same, but at the end of the day, P inverse AP would have still equaled J. So it would have been a different answer, but it would have been a different right answer. Yeah. It's the same way how like even when we did PDP inverse, remember when we did A equals PDP inverse? There was no rule on what order to put the eigenvectors in P, right? It doesn't matter if you put V1, Vn, or like start with V2 or whatever, as long as your diagonal matrix had the corresponding eigenvalues in the same order, right? So like the first eigenvalue had to be matched with the first eigenvector. So you could have a bunch of different answers. All of them are going to work. Just make sure that they're aligning, they're matching up. Okay, let's look at the second example. Second type of problem, which is like this. Okay, let's read this problem. This is where you're usually going to see bigger matrices, 6 by 6s, 7 by 7s, and they're not going to ask you to find P. They're just going to ask you to find J. So this is where our dot diagram is going to be like life-saving. I think this is pretty fun. It's like a very simple puzzle once you realize. So let A be a 7 by 7 matrix. Okay, so let's find the Jordan form of A. So let's leave space for our answer. 7 by 7 matrix. Okay. Its characteristic polynomial is given by lambda minus 2 to the 7th. Okay, I'm going to do the dot diagram here on the side. Okay, so lambda minus 2 to the 7th. That means we have lambda equals 2 with algebraic multiplicity equals 7. So already I know my only eigenvalue is 2. Okay, there could be a case where, let's say, for example, the characteristic polynomial was lambda minus 2 to the 4th times lambda minus 1 to the 3rd. Then you have lambda equals 2 with algebraic multiplicity 4, right? And then lambda equals 1 with algebraic multiplicity 3. Then your dot diagram, you would split it up into two parts. You would say, here's my dot diagram for lambda equals 2, and here's my dot diagram for lambda equals 1. And then you need to do it individually for each part. So you'd first do like this part. This row would be A minus 2i or 1i, depending on which one you're doing. And I think we have an example of that later on. But for now, we're lucky. We're going to have the simpler case, which is just where, okay, which is just where lambda equals 2. That's our only header for the dot diagram. And let's make 3 lines. Let's make them straight. Hmm. Okay, I'm gonna go up. I'm like reaching the bottom of my tablet, so it's very hard to make straight lines. Okay, I'm gonna do it up here. Lambda equals 2. Mm, 1, 2, 3. Okay. Remember, this is gonna be a minus 2i, the nullity of a minus 2i. This guy's gonna be the nullity of a minus 2i squared, and this guy's gonna be the nullity of a minus 2i cubed. Okay, the characters from both. Okay, dimension of the null space of a minus 2i equals 3. In other words, right, nullity of a minus 2i equals 3. Perfect. That's a great start. That means we have 3 bases for our tower, right? We're not going to build up because we haven't even talked about a minus 2i squared. We're only building on the bottom row. Okay, 3 bases. Then dimension of the nullity of a minus 2i squared, and now we're on the above row, is 5. Now the question is, we're not going to add 5 new ones because then we have 8 total. We need to end up with 5 total. So we already have 3. We gain 2 more to make 5, right? And the reason why is because any vector in the null space of this is already going to be in the null spaces of this. Because if a vector satisfies a minus 2i times that vector equals 0, right? Then a minus 2i squared times that vector also has to be 0. Because a minus 2i squared can be written as a minus 2i times a minus 2i times the vector equals 0, and this is already equal to 0 from before. So all that is to say is that these are going to be overlaps anyways. That's why we don't do 5 new ones on the top. Okay, that's good. And then the last thing we found out is that dimension of the nullity of a minus 2i cubed equals 7. So that means that up here I'm going to add 2 more to get to 7, right? And I'm not going to add 1 here and 1 here because then this is a floating dot. So they have to build on top of each other, and boom. Now we can immediately find j. Why? Because that's kind of the helpfulness of the dot diagram. A 3 by 3 Jordan block, right? A 3 by 3 Jordan block and a 1 by 1 Jordan block, all with lambda equals 2 in this case. So let's do that. Let's do a 3 by 3 Jordan block. So let's first put 7 2s along the diagonal. 4, 5, 6, 7. Okay. First Jordan block 3 by 3. So what's that going to look like? That's going to be like this part isolated. So it's going to have 2s along the diagonal, 1s along the super diagonal, 0s everywhere else. And then the next one, make sure to not put a 1 here. That would be wrong, right? It's a 3 by 3, and then we cut off. Then we have our new 3 by 3 here. So our first one is going to start here. So this is going to be 1, 1. And then don't put a 1 here because right, this is our second 3 by 3, and then we just have a 1 by 1. So that's it. So that's everywhere else is going to be zeros. So 0, 0, 0, zeros everywhere here, 0 here, and then always zeros underneath. Okay. Guaranteed on the placement exam, 1 to 2 questions will be Jordan canonical form. Guaranteed. It's like it's a little bit not strange. This is a difference in our course at Penn. We spend a lot of time on Jordan canonical form compared to like some other traditional linear algebra courses. Um, all right. Any questions about that? This is an example of going that, right? Same dot diagram. Um, yeah. 3 by 3, 3 by 3, and a 1 by 1. And then you assemble it. Nice. Okay. Here's some practice problems. Ideally, let's save these towards the end because this is just going to be computation like intensive. We'll do them at the end if we have time, but I don't want to waste time. Um, these are like the 2 examples. I mean, like Jordan canonical form is just doing these 2 problems. Okay. Actually, this one is fairly simple to see if this is a good example of a double one. So take 2 minutes and try and do this one, like on your own. Try and make the dot diagram. Like actually try and do it yourself because like you see someone do it and you're like, oh, this makes sense. But there's a few like nuances that it's good to just to do one practice. Okay. So here we have let's do this one a bit quickly. Lambda equals 3 and lambda equals 2. So we're going to split into lambda equals 3 and lambda equals 2. Okay. The nullity of A minus 3i equals 2. So we're only dealing with the left side for now. So here's, I'm not going to write 3i, I'm going to write minus lambda I, because right, lambda will depend on whether we're dealing with the left case or the right case, but just so it doesn't get confusing, A minus lambda I squared, and it looks like we don't even need A minus lambda I cubed, but whatever. Okay, so the nullity of A minus 3i equals 2. That means I've got 2 here. The nullity of A minus 3i squared equals 4. That means I need to, over here on top for the 3, I need to get 2 more to get up to 4. So that's right there. And then the nullity of A minus 2i. So now I'm completely resetting into a new set situation. The nullity of A minus 2i equals 2. So 2 blocks down here. Okay. So then you can see my final Jordan form will be a 2 by 2, right? And this will have lambda equals 3. Another 2 by 2 with lambda equals 3. Then a 1 by 1 with lambda equals 1 by 1 with lambda equals 2, and then one more 1 by 1 with lambda equals 2. Let's draw that, right? It's going to be a 6 by 6 matrix. So 2 by 2 and 2 by 2 with lambda equals 3 means that I'm going to have 4 3s along the diagonal, and then 2 2s. Correct? And then I have 2 2 by 2s. So this is going to be my 1 2 by 2 for 3, and this is going to be my second 2 by 2 for 3. And then the 2s are all 1 by 1, so 1 by 1 and 1 by 1. So that's going to be a 0 in between here, a 0 here, a 0 here, zeros everywhere else. So notice how, like, if you think about this problem in two situations, the 3 part has Jordan form going on, but the 2 part is actually cleanly diagonalizable. And that's because, like if you think about it, right, lambda equals 2 has an algebraic multiplicity of 2, but check it out, the geometric multiplicity, as in the nullity of A minus lambda I, oh shoot, this says lambda minus 3i. It should be A minus 3i here. Whoopsies. Um, yeah, there should be A here, not lambda, by the way. Um, anyways, the idea is there. The algebraic multiplicity is 2, and the geometric multiplicity is also 2, because we get 2 eigenvectors just in this row. So that's why, like, this section of the 2 is kind of diagonalizable. Um, if we wrote, yeah, if you did 2 on the left and 3 on the right, you would have the correct J matrix again. Would also be it would also be correct. No, the J matrix, the order can be permuted, but what would matter is like your P matrix would technically change, right? This one is going to have a P matrix with a slightly different order compared to your answer, but in this problem, they're not asking for the P matrix, so that would also be correct. Yeah. Yes, good question. Okay. Next, let's do this chapter and then take a break because I want to make sure we finish everything. Is everything clear with Jordan form? Any questions on Jordan form? Okay. Now we're gonna get into like this is kind of a strange section. Um, it's a little bit out of nowhere, but it's pretty interesting. So this stuff you can read. It's a introduction to what the dot product is, right? You guys should all know the dot product from multi. Like 1, 2, 3, dotted with 3, 4, 5 is this times this, plus this times this, plus this times this, right? The inner product is a generalization of the dot product. So in, normal real number settings, right, the inner product is just a dot product, right? The only thing is the inner product usually extends to like complex numbers and other, sets of numbers. However, it's just a more general version of the dot product. So you can think of them for this course, you can think of them interchangeably, and that helps with intuition. Okay. So the first thing that's important to know and the first nice use of inner products is in projections. So if I have a vector v and I want to project it onto u, what does that mean? That means I have some vector v that looks like this, okay, and I have a vector u which looks like this. I want to find the portion of v. Remember, any vector v can be broken up into two components, right? This v can be broken up into the sum of a vector that goes like this and a vector that goes like that, right? One of them is perpendicular to you and one of them is in the same direction as you. I want to find this guy. This guy, this vector right here, is the projection of v onto you. So the way we write that is like this. the projection of V onto U. Okay, so this means projection of V onto U. Okay. The formula is given right here. It's the it's the inner product. See, I haven't said dot product. I might slip up and say dot product. They're the same thing in this scenario, so don't worry about that. It's the inner product between V and U divided by the inner product between U and itself multiplied by the original vector U itself. Okay? Before we think about where this comes from, the idea that we're saying here is think about what a dot product and inner product will return. Two vectors, inner product is always going to be a scalar, right? So this is going to be a scalar. This is going to be a regular number. This is going to be another number. So this division is also going to be a number. So all we're saying is the projection of V onto U is some number times U, which is good, right? Because it's basically going to be some number times U. And that number will tell us, okay, either we're going to scale U to like a small amount, or we're going to take a lot of U if it's like 1.5 U or whatever. But it tells us that our direction is right. So that's a good sign. Okay. Intuition wise, it's nice to know that the dot product and the inner product can be split up. There's a formula that says that U inner product with V equals the magnitude of U times the magnitude of V times the cosine of the angle in between them. So theta is the angle in between them. This is probably something you saw in 1410 or in like any multi-class, I guess. And so if we use that formula, right? If we use that formula and plug in, so we plug in U, V and U becomes magnitude of V, magnitude of U, cosine of theta 1, where theta 1 is the angle between V and U, and theta 2 here is the angle between U and U. Notice that the angle between U and U is 0, and cosine of 0 is 1, so this part goes away. Then we can cancel out a magnitude of U here and a magnitude of U here. And then we can take this magnitude of U and bring it out and divide it out here. And we're left with this expression for the projection of V onto U. So all we're saying, right, is that U divided by its magnitude finds us a unit vector, right, in the direction of U. So this is the unit vector in direction of U. So this is basically just a direction. It has no size to it. It's just a direction. It's telling us which way to point. And this guy, V cosine theta, tells us how much we want to point. So U looks like this. This is what U, that's what that U looks like, the unit vector U. And this V cosine theta term just comes in and tells us, okay, either go bigger or go smaller or go huge or whatever. Okay. So, and where does V cosine theta come from? If you think about it, if this angle is theta here, right, and this is V, the magnitude of V is the length of this side here. And then the magnitude of the length of this side will just be V cosine theta by trigonometry, right? Because this splits up into V sine theta and V cosine theta. Not as important for this course, so I'm going to stop, blabbering about this stuff a little bit, but it's good to intuitively get what a projection means, okay? Now, there's a new phrase we're going to learn, which is, what does the word orthonormal mean? We use it to describe a set of vectors. A set of vectors is orthonormal if they're all first orthogonal and normal. So orthonormal, as you may guess, right? Orthonormal is a combination of orthogonal, which means perpendicular, right? Another way of seeing perpendicular is that the dot product between inner product between A and B equals 0, right? That's what perpendicular means, right? Because the inner product between A and B is magnitude of A, magnitude of B, cosine theta. And if they're perpendicular, then theta is 90 degrees, and then cosine 90 is 0. So that's why that comes out. And normal just means unit vectors. Unit. So length of 1. Normal means a length of 1. So an orthonormal set of vectors is a set of vectors that are all orthogonal to each other. So if I have 3 vectors, right, v1, v2, and v3, and they're orthogonal first, that means that v1 and v2, their inner product is 0, v1 and v3, their inner product is 0, and then v2 and v3. So all possible combinations are 0. If it's additionally orthonormal, that means that the magnitude of each of my vectors is 1. Okay, so they're all unit vectors. Okay, an orthonormal basis is just a basis that is orthonormal, where all the vectors are orthonormal to each other. So the standard basis for R3 is an orthonormal basis because it's all the vectors are perpendicular to each other, correct? Right? If we think about 3 dimensions, right? Our standard basis for R3, like one vector goes this way, one vector goes this way, and one vector goes this way. They're all perpendicular and they're all normal. length 1. So this is kind of the reason why we care about orthonormal bases is because they're just easier to think about, right? When your basis vectors are perpendicular, you can easily envision the space, right? Versus if I drew my basis vectors like one is this way, one is that way, and one is this way. You're like, what's going on? Like, obviously you can still make any vector in 3D, but it's just more confusing, right? All right. So anyways, how do we now we're going to learn that the main part, the main relation to the actual course here is that we're going to learn a way of taking any set of linearly independent vectors, okay, and turning them into an orthonormal basis. Okay, so it's a pretty cool trick. The way it works is also quite interesting. So let's say, okay, let's look at what this formula is doing. So remember, the goal is we're given any set of linearly independent vectors. So maybe like 1, 2, 1, negative 2, 3, 4. I don't even know if these are linearly independent. Let's hope so. That these are three linearly independent. We'll turn it into a new basis that will still span R3, but now it'll be orthonormal. Okay. It's not necessarily going to be the basis we had before, but we'll see. Okay. Let v1 through vn be the original vectors. So these are like our v1s, v2, v3. And let u1 be the vectors that we're going to slot in here. So our goal is to find u1, u2, u3, etc. Okay. Um, the first thing we say, okay, so again, the goal is to find an orthonormal basis. We're going to split that into two steps. First, we're going to find an orthogonal basis. So we're going to make sure all the vectors are orthogonal to each other. Then we're just going to normalize by dividing by the magnitude. So for now, ignore the normal part. No big deal. Okay. The first thing that we say, okay, u1 equals v1. So the first vector in our new basis is going to be the exact same vector as the previous one. Okay. Then we say u2 is v2 minus the projection of v2 onto u1. So u2, we take v2, our old basis vector, and we subtract off something. What are we subtracting? Its projection onto u1. In other words, it's similarity, right? When I say project, let's say v2 onto u1, I'm finding the portion of v2 that's similar to u1, and in this case, we're subtracting it off. So then we're only left with this part of v2. That should make sense, right? That's why now this new part, so here's v2 originally, right? Here's the projection of v2 onto u1. And if this part, how would I write it? I would say, okay, this is v2, my original vector, minus the projection of v2 onto u1, right? And this is the vector I want, right? I want a basis vector that's perpendicular to my original u1 right here. So that's why this is going to be my expression for the second u2, right? This is going to be my expression for what I'm going to put in here. Similarly, u3, I'm going to take v3. So now it's in 3 dimensions, so I'm not going to draw it. But I'm going to take v3. I'm going to minus its projection onto u1. So I'm going to remove all the similarities between u1. I'm going to remove all the similarities between u2. And what's left, everything will be perpendicular, right? Everything is going to be perpendicular to both u1 and u2 because I removed all the parallel components. Then you get u3. Then you're going to be left with 3 vectors here, whatever. This is obviously not the right answer, right? 1, 0, 1. And then to find the final answer, you just take all of these and make them normal. And remember, to take a vector v and make it normal, you do v divided by its magnitude. Okay. Let's walk through an example. Okay, so here are 3 vectors. And we want to find an orthonormal basis of them. Okay. So again, u1 equals x1. So it's a little bit confusing that I called them x1 here when they were v1 before, but like there's no guarantee that the problem is going to also use v's. So it's good to it's good to see a different example. So u1 is x1. Done. Okay, so let's make space for our u1 is x1. Then u2 is x2 minus the projection of x2 onto u1. So x2 minus I'm going to skip writing the vector sign because it's going to annoy me, but these should all have vectors above them. Minus the projection of x2 onto u1. So what is the projection of x2 onto u1? We know that formula. So it's going to be x2 minus. Remember, we do x2 inner product of x2 with u1 divided by the inner product of u1 with itself times u1. And this u1 must be a vector. So this part gives you a scalar, but then you multiply that scalar by a vector. So that's why this whole result is actually a vector. And x2 is a vector itself. That's how the arithmetic works. So be careful with arithmetic. So again, we do that here. We do all the math here. You should be able to review and it should make sense. I won't go. Actually, let's do the math for one, just so we can see. Let's find x. Let's find u2. So we're saying u2 equals this guy, which equals that guy. So u2 equals, okay, x2. X2 is 1, 0, negative 4 minus, okay, x2 inner product with u1. So x2 inner product with u1. That's going to be 1 times 1 is 1, plus 0 times 2 is 0. So 1 times 1 plus 0 plus negative 4 times negative 2 plus 8. That should be 9. So 1 plus 0 plus 8 is 9. So this part is 9 here. Then u1 dotted with itself is going to be this guy dotted with this guy. So 1 times 1 is 1, 2 times 2 is 4, and 2 times 2 is negative times 2 is 4. So 1 plus 4 is 9 again. 9 over 9 times, and this whole thing, remember, u1 is a vector itself. So 1, 2, negative 2. Okay, so 9 over 9 obviously becomes 1. This becomes 1 times this vector. So we're basically just doing this vector minus this vector. And then we get that u2 equals 1 minus 1 is 0. 0 minus 2 is negative 2. And then negative 4 minus negative 2 is negative 2. Right? And hopefully let's check that u1 and u2 are now, they should be orthogonal to each other, right? If I take u1 inner product with u2, I should get 0. And I do, right? Because 1 times 0 is 0. 2 times negative 2 is negative 4. And then plus negative 2 negative 2 plus 4 gives us 0. Okay, so good. Same way, you'll do the same thing with an extra step, right? So remember for u3, right, it's a little bit trickier because you not only have to subtract the projection of x3 onto u2, but also u1. So not just onto u1, but also onto u2, because now you're building new vectors in your basis and you have to remove the similarities from all of them. Okay, so just a bit more math, make sure you can follow through. And then we get these three vectors. Then we just normalize them. Okay, so if you go to like a YouTube video, sometimes the like people will say, okay, you should normalize after each step. That means to find u1, you take x1 and you normalize it. Then after you find u2, you normalize it again. But honestly, that seems it's a bit unnecessary because why do you have to normalize it and then you're doing more math on it anyways? Might as well do all the arithmetic, get your three vectors, and then normalize them. Normalize by dividing by the magnitude, and that's your answer. So that's what the Gram-Schmidt process is. It allows you to take a set of linearly independent vectors. They must be linearly independent to begin with, and turn them all orthogonal to each other. And then finally, you can normalize and turn them orthonormal. Okay, any questions about Gram-Schmidt? Okay, let's finish this unit. Yeah, let's finish this unit and then take a break. Okay. This is more important. So the really the only thing to remember from there, the projection unit should be Gram-Schmidt. And then sometimes intuitively, like what's the idea of a projection? Other than that, not much. All right. So now we get into self-adjoint transformations. Okay. Remember, matrices, linear transformations can be represented as matrices. Okay. So a linear transformation can be represented as a matrix. Okay. There's a specific type of transformation called self-adjoint transformations, and that happens when your matrix is symmetric. Okay, so if a matrix is self-adjoint, if a linear transformation is self-adjoint, that just means symmetric. For the purpose of our course, all that means is that A is symmetric. Okay, remember, symmetric, like intuitively, you can usually tell. If I have 2, 2, 1, 1, okay, symmetric, right? It looks, this is a mirror along my diagonal, everything to the right and to the left is good. Not good is the same. Okay. The formal way of saying symmetric is that A equals A transpose. Right. That's the definition of symmetric. And if you quick review from last time, remember A equals negative A transpose means skew symmetric. So those are two important matrices to know. But symmetric is what we're going to deal with now. Okay. So there's a very nice theorem. Okay. First of all, there's a new word we're going to learn more like jargon. Spectrum of a matrix is just a set of eigenvalues. So if I wanted to say like, oh, hey, give me all the eigenvalues of A, I could also say, oh, hey, give me the spectrum of A. More words to like be familiar with. Okay. So if we have an n by n matrix that is symmetric, then it has the following properties. So a symmetric matrix has some really nice properties. A has n real eigenvalues. That means that no imaginary eigenvalues. So when we solve A minus lambda I equals 0, determinant of A minus lambda equals 0, and we get our like lambda minus 2 squared blah, blah, blah equals 0, lambdas will always be real numbers, no i's at all. That's nice. This one's very nice. GM equals AM for each eigenvalue. And to be honest, I shouldn't have even put 2 and 3 in the same one because these mean the same thing, right? They imply each other. If GM equals AM for all eigenvalues, then A is diagonalizable. This is really nice. This tells us that a symmetric matrix, right? An n by n symmetric matrix is always diagonalizable. We never have to worry about Jordan form. Okay? So that's the first sort of stage of it. There's two additional things that's sort of new to our unit. All the eigenvectors are mutually orthogonal. This is also great. Okay? That means that when I form my P matrix, right, and I put V1 and V2 all the way to Vn, right, these are naturally going to be mutually orthogonal. This is a bit of a lie here. Not always, okay? This is only if, this fourth scenario only happens if you have algebraic multiplicity of 1 for all your eigenvalues. As in if you're dealing with a characteristic polynomial like this, where there's no squares or cubes here. Okay. If you have squares and cubes, then they may not all be mutually orthogonal, but we know a way of making them mutually orthogonal, which is Gram-Schmidt. So we'll talk about that later. And then the final thing is A is orthogonally diagonalizable. So what does that mean? We know what diagonalizable means. So regular diagonalizable means that A can be written as P d P inverse, where P is V1 through Vn, and D equals lambda 1 through lambda n. I've written this a lot, but it's also for like repetition purposes. This is like really important. You should know this, like you should know this very cleanly, and you should have a good understanding. Okay. What does orthogonally diagonalizable mean? Same exact thing with one extra condition. It means A equals P dP inverse, where P equals V1 through Vn, and D equals lambda 1 through lambda n, and P is an orthonormal matrix. Okay, what does orthonormal matrix mean? It just means that all of the columns are orthonormal to each other. So it's basically regular diagonalization with an additional specification that says that to orthogonally diagonalize something, you can't just give me P, you have to make sure the columns of P are orthonormal, orthogonal and normal. Okay, now this is why 4 is quite nice, is because for most of the cases when algebraic multiplicity equals 1, all the eigenvectors are going to be mutually orthogonal in the first place. So then you just have to normalize them, and then you can get your A equals PDP inverse. Okay, there's a nice and then to finish that, right? If algebraic multiplicity equals 2 for whatever reason, for an eigenvalue, then there's a chance that all your vectors might not be orthogonal to each other, but then all you have to do is run Gram-Schmidt. And you should be able to run Gram-Schmidt and get orthogonal or orthogonal vectors at the end. Okay. And we'll see examples of both of those. Okay. An additional thing that's very important is this statement right here. If a matrix P is orthonormal, okay, so if P is orthonormal, that means that P times its transpose equals the identity. Okay, and this should make sense because think about what P being orthonormal means. It means that, right? Let's actually write out the multiplication. So I'm going to write out the vector. So P is going to be, right, let's do 3 vectors. V1, V2, and V3, right? And then P transpose is going to be V1, like the rotated, right? Because it's transpose, V2, and V3. Okay, what happens when I do the matrix multiplication? Okay, I go row by column. I should have drawn it the other way. But anyways, I do like this column by this row, right? And that's going to be VI, right? The inner product of VI, V1, and V1. And because they're orthonormal, this is going to be equal to 1, right? Because V1 has magnitude 1, and it's obviously like you can think about it as like V1 dotted with V1 is magnitude of V1, cosine of 0, which is 1, and we know the magnitude of v1 is 1, so this equals 1. That means like my first element is going to be 1 here. But any other element, so obviously v2 dotted with v2 is also going to be 1, and then v3 dotted with v3 is also going to be 1, and those are going to be along the diagonal. But any other combination, like if I do v1 multiplied by v2, that's going to, or dotted with v2, that's going to be 0 because they're orthogonal to each other. Okay, so that should make sense why eventually we'll get out the identity as our answer. So in that case, right, if we know P times P transpose equals the identity, right, that means that right, P transpose equals P inverse. In the sense that, right, an inverse means that an inverse matrix A and its inverse have the property that A inverse equals 1, equals identity. So in this case, right, A is P, and if multiplying by P transpose gives the identity, that means that P transpose must be also equal to P inverse. Okay, so in our orthogonal diagonalization, we can say, okay, A equals PDP inverse, or we could say A is also equal to PDP transpose. Those are both equivalent. Okay, that's the point of orthogonal diagonalization. So it's really just normal diagonalization with a bit of an extra step. So let's do an example. Orthogonally diagonalize a symmetric matrix. So we first find the eigenvalues, which I skipped the steps for, but we get lambda equals 1, lambda equals -1, and lambda equals 4. Then we find the eigenvectors. So we do that doing A minus lambda I same way. Then we form our matrix P and our matrix D. Remember, this is just like this is vanilla eigen diagonalization, right? Make sure they go in the right order. So -1, eigenvalue -1 corresponds to this eigenvector. So that comes first, then second one, then third one. Okay. And you may think we're done, but remember, we're orthogonally diagonalizing, which means that we want A equals PDP inverse equals PDP transpose, either one, where P is orthonormal. So it looks like our P is not orthonormal, it's orthogonal right now because of the spectral theorem. It says that, but it's not orthonormal. So let's normalize each of the columns, as then take each column and divide by its magnitude to get P, and that's P, and D is up there as usual, up here. Okay. Now the nuance is that let's say here it was nice, right? Or we had algebraic multiplicity of 1 for each of the eigenvalues, right? But if we had algebraic multiplicity of 2, then there's a chance that these are not actually orthogonal to each other, as in maybe these two are not orthogonal. Run Gram-Schmidt on the whole thing. Run Gram-Schmidt process on the whole thing, and then you'll end up with an orthogonal set. Then you can normalize it and get your final P. Okay? Any questions about orthogonal diagonalization? Okay, the next part is spectral decomposition. I highly doubt a question on this comes up, but there's always a chance that it's like a part of a question and it's very like straightforward. Remember, we said okay, ignore the notes text, let's do it on the side. So we know that if a matrix is orthogonally diagonalizable, that means that A equals PD P transpose. Okay, so let's write it out. Actually, we'll just use here. So A equals P, right? P is, here we're using U1 for our orthonormal eigenvector instead of V, just a change in variables, using a different variable. So U1, right, is a vector. U2 is a vector, all the way up to UN is a vector. So that's our P matrix. Our D matrix has eigenvalues all along the diagonal. And then P transpose, right, you just take every column and turn it into a row. Every column turned into a row, right? So really what this represents, this is actually a matrix, right? It's not a vector. It's a vector of vectors, which is a matrix. Okay, so that's that. Now let's see, we're going to do some algebra out. So if we multiply, I'm going to go quick over this because it's not very crucial, right? But if we first multiply these two together, right, we're going to do every row by every column. So we're going to dot those together. So it's just going to really be left with ui times lambda I, right, over here, and then all the way down. And then we're going to dot it with this last part, one more multiplication. And then we get this result, right, that we're doing lambda I times eigenvector 1 times its transpose, plus lambda 2 eigenvector 2 times its transpose, right? And if you notice, right, eigenvector 2 times its transpose, or eigenvector times its transpose in general, is going to give us a matrix actually. Because if you think about what U1 looks like, let's say U1 looks like 1, 2, and then its transpose, right, is going to be 1, 2. This is not actually going to be a number. It's going to be, this is a 2 by 1 matrix multiplied by a 1 by 2 matrix is going to give us a 2 by 2 matrix. So that's going to be like 1 times 1 is 1, 1 times 2 is 2, 2 times 1 is 2, and 2 times 2 is 4. Okay, so what we're saying is that our original matrix A is split up into some eigenvalue times the matrix plus some eigenvalue, a new eigenvalue times another matrix. So basically what we've done is we decomposed A based on its spectrum. Spectrum means eigenvalues. So we've decomposed A based on its eigenvalues. That's why it's called spectral decomposition. Because we've taken A and we said, okay, it's expressed as its first eigenvalue times a matrix plus its second eigenvalue times another matrix, all the way up to its final eigenvalue times another matrix. Why could this potentially be useful? Because maybe you're looking to, A is like an image file and you want to compress it and you want to get rid of some of these, right? So you can choose like the lowest eigenvalues, you can get rid of them. There's no need for them and you can only save these and it'll reduce your storage potentially. This is like a potential use. So here, clearly an example, right? A is this. Remember the formula, all you really need to know is the formula is that A equals lambda 1 times eigenvector 1 times eigenvector 1 transpose plus lambda 2 times eigenvector 2 times eigenvector 2 transpose, right? These are all vectors. These guys are vectors. So here, let's put that in, right? Here's our A. We know we have eigenvalue 1 equals -8. Eigenvector 1 equals 1, -1. And then eigenvalue 2 equals 4. And then eigenvector 2 equals 1, 1. Then we just plug into the formula and it's fairly straightforward, right? And you should see that this is our spectral decomposition, right? Eigenvalue times the matrix plus eigenvalue times the matrix, and it does end up equaling the original if you add it out. Okay, last thing, let's do a quick summary. So for regular diagonalization, that's when we're saying, okay, A has to equal PDP inverse. For orthogonal diagonalization, we're saying, okay, A equals PDP inverse, sure, but also A equals PDP transpose. Those are the same, okay? To do regular diagonalization, A must be diagonalizable, right? Which means AM equals GM for all eigenvalues. To do orthogonal diagonalization, A must be symmetric. So when they ask you to orthogonally diagonalize a matrix, the matrix they give you will always be symmetric. Otherwise, you can't do orthogonal diagonalization. And then finally, the requirement for P in regular diagonalization, P is your eigenvalues that go like this, right? And then in orthogonal diagonalization, P is again your eigenvalues, but they're orthonormal to each other. All the columns are orthonormal. And then D is the same for both of them. So D is always easy to figure out. Okay, here are some practice problems. I think let's take a break now, because the next thing we'll get into is differential equations, and that's quite a lot of material. So let's take a break. You can try these practice problems. The solution should be posted as well, but it's good to do a practice of both of these because it's just entirely computation. But let's come back at 4:20. Okay. Any questions, just put in the chat and let me know. Okay, we can come back to start differential equations. Um, all right. So the beginning of this should not be too bad. Honestly, the thing with differential equations is it's more of like you just have to know how to do it, and then it's like you have to do the process a few times to like lock it in your head, and then it's doing the same thing over and over again with different numbers. There's not much like creative thinking you need. Okay, so the first term you're gonna hear is the order. So a second order differential equation has the highest derivative of like a second derivative. So a fourth order has a fourth derivative in it, as in y prime 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 prime. Okay. Um, first order ordinary. So ODE stand with ordinary differential equations. Ordinary means that everything is a function of one variable. So just you're gonna hear me say ODE instead of differential equations every time. It's just like language that makes it easier. So um first order ODEs have highest derivative of one, and they take the form y prime plus something times y equals something. Okay. There's two ways of solving them. The first way is the nicest way that you guys should have seen if you took even BC Calc, goes over like for separable differential equations. Let's do an example real quick, right? All you do is, oh, I can zoom, let me zoom in a little bit. Hold on. Okay. Um, all you do is okay, x squared y prime equals x plus 1 prime, x plus 1 times y. Bring the y's and the dy's to the other side. So first you write y prime as dy dx. And so you get x squared dy dx equals x plus 1 times y. Then we bring the y's to one side and the x's to the other side. So y comes over here and we get dy over y, as in 1 over y dy equals x plus 1 over x squared dx. Integrate both sides because now we've got a dy and a dx. You integrate both sides, the dy's go away, and you integrate 1 over y to get ln of y. Integrate x plus 1 over x squared. You can do this by splitting up the fraction, right? X plus 1 over x squared is x over x squared is 1 over x plus 1 over x squared is x and negative 2. Integrate, do the algebra. We won't review that here. It is a good idea to brush up on your integration techniques. Just know how to do like a simple u substitution or maybe even how to integrate by parts. I doubt that will come up, but you want to be prepared either way. Also, it's like a good general skill to know how to integrate by parts that you tend to forget if you don't do it for a while. Okay. The second way is okay, what happens if we can't separate the y's and the x's so easily? If you look at this example here, dy, if we write y prime as dy dx, it's not evident how to bring x's and dx's to one side and y's and dy's to the other side. So here's where we use this thing called the integration factor. Okay, maybe you have learned it. This is what the integration factor equals. Okay, it's a very cool idea. Um, so you have to first always think of your original equation as y prime plus p of x times y equals q of x. Okay, so if you can write your original equation like this, then your integrating factor is e to the integral of p of x dx. Okay, and we'll see why this works. So let's say we're trying to solve this differential equation. First, we put it into standard form. So we need a 1 in front of the y prime. So we divide out by x squared. And this becomes our differential equation. Now we notice that p of x equals 1 over x, which is going to be important for our integration factor. Why? Because to find the integration factor, we do e to the integral of p of x, so 1 over x dx, right? This just becomes e to the ln of x. Absolute value should be fine. We can ignore that for now. And e to the ln cancels and we get out x. That means we get an integrating factor of x. Now that we have this integrating factor, what do we do with it? We multiply the left and right sides of the equation by the integrating factor. And this allows for a very neat thing to happen. Look what happens when we multiply the left and right when we multiply the left and right hand sides by the integrating factor. So we take this equation that we had here, multiply by x on the left and the right. So on the left, we get x times y prime plus y equals 1 over x, right? And then if you notice the left hand side, once you multiply by the integrating factor, whatever it is, it will always be able to be written as the integral of as the derivative of a product. So if we think about what xy prime plus y equals, right? It's the derivative with respect to x of x times y. Actually, right? If you do the product rule, it's sort of, you just have to reverse engineer a little bit and think, okay, I always think of the product rule as derivative of the first times the second plus the first times the derivative of the second. So this is like first times the derivative of the second. So the first would be x and the second would be y. And so that's, that's your expression, right? So anyways, either way, the power of the integrating factor is no matter what, that this is going to be written into the derivative of a product of two terms, right? And so now we have that, we take this left-hand side and rewrite it as the derivative of a product. Then integrate both sides, get rid of integrate both sides dx. And because we're integrating a derivative, they undo each other, and we're left with xy equals, and you can integrate the right side and solve for y. Okay, so that's how you use the integrating factor. You'll see examples of it come up in practice problems. There's two words to learn: homogeneous and non-homogeneous. Homogeneous means that you're solving this type of equation where your right side is 0, and non-homogeneous means that your right side is not 0. As in, the constant term is 0 or not 0, homogeneous, non-homogeneous. Okay? Again, that's for first order differential equations. For second order, all that happens is we end up having an extra double second derivative here. But homogeneous and non-homogeneous have the same idea. Homogeneous second order ODEs have the form y double prime plus p of ty prime plus q of ty equals 0. And then non-homogeneous, instead of having 0 on the right, will have some term here that's either a constant or a function of t. Notice how here we switch from like y being a function of x to now y being a function of t. There's no reason for that. It's just that you can see both pop up. You can see anything pop up. So it's good to get familiar with everything. Okay. The first type of second order ODE that we'll learn how to solve is called constant coefficient systems. Not systems. Constant coefficient second order ODEs. That's when all of these coefficients are constant numbers. Okay. So actually this guy doesn't have to be. We'll figure that out. But P of t and Q of t are going to be constants, like 2 or 3 or 4 or 5 or whatever. Okay, so let's see how we solve those. Okay. Oh, before we talk about that, when solving any ODE, actually, any ordinary differential equation, okay, specifically in our case for second order, ordinary differential equations, the solution is always given by y equals yc or yc plus yp. Okay. Why do we do this? What does this mean? Yc is the complementary solution, i.e., is the solution to the homogeneous differential equation. Yp is the solution to the particular differential equation. Let's see what this means. If we had an example where we're trying to solve y double prime plus 5y prime plus 6y equals 7 sine of x. So soon, in 10 minutes, you'll be able to actually solve this. But the steps for solving this is you first say, okay, is this homogeneous? No, it's non-homogeneous. So my solution is going to be broken up into two parts. First, I'm going to solve for yc. How I'm going to solve for yc, the complementary solution, I'm going to turn this into a homogeneous equation. So I'm going to solve for y double prime plus 5y prime plus 6y equals 0. And I'm going to solve for yc this way. Then on the right side, I'm going to solve for yp by actually solving this differential equation. And we'll learn ways to do both of these steps. Okay, but I'm actually going to solve this, and I'm going to get yp. Okay. Then your overall solution is just going to be this guy plus this guy. Now, this is a bit counterintuitive because it's like, okay, to solve this, why don't I just need to solve this? Why do I have to add yc? And the logic for that is explained down here. It's just a bit of algebra and rearranging, and you should see that adding yc is like adding 0. Because an intuitive way you can think about it is like yc turns this differential equation into 0. So adding it a bunch of times doesn't matter. It's just adding 0 a bunch of times. So it won't change your equation or your result. But you can read the explanation, okay? Now, let's actually solve some of these. The first one is constant coefficient second order ODEs. So those are of the form y double prime equals ay prime plus by, y double prime plus ay prime plus by equals 0, where a and b are just numbers. Okay. Now, the nice thing with these is that the guess, basically the idea with differential equations is we want to take a guess at what the solution should be. Okay. Now, if you think about what we're saying, is we're saying, okay, a function y, its second derivative plus something times its first derivative plus something times itself must equal 0. So that means that these, like y double prime, y prime, and y somehow have to cancel each other out, right? Like if y double prime is sine of x, and then y prime is cosine of x, then those are never going to cancel out, right? Sine of x plus a times cosine of x is never going to cancel out. So a good guess would be, let's guess y equals e to the rt. Why? Because if y equals e to the rt, then y prime equals r e to the rt, and then y double prime equals r squared e to the rt. Right? And because all of these are of the form e to the rt, something times e to the rt, there's a good chance that they can be canceled out depending on what we choose r to be. Okay, so let's plug in that guess and see what happens. So we guess y equals e to the rt. We plug it in, and then we get, okay, so remember, y prime is this, and y double prime is this. So pretty much what we get is that y double prime, that guy, plus a times y prime, plus b times y equals 0. And we can divide by e to the rt on both sides. So getting rid of these e to the rt's leads us to solving this equation. And this is a simple quadratic equation because remember, we're going to know what a and b are. That's going to be given to us in the problem, right? So now we're just going to solve this quadratic equation for a and b. And then let's say we get r equals 2 and r equals 3. Then remember before, our guess was e to the rt, right? That means our one solution is going to be e to the 2t, and then any multiple of that. And then our next solution is going to be any multiple times e to the 3t, and then we're just going to add these two solutions up to get the overall solution. Okay, there's a nice chart that summarizes this, and that's right here. So this chart is exactly what should go on your cheat sheet because you are given a cheat sheet for this exam, so I would take advantage of that and put all of these differential equation charts on your cheat sheet. So what is this saying? We're given some equation, y double prime plus ay prime plus by equals 0. Okay, we're first doing the homogeneous case. We're not talking about non-homogeneous yet. What we do is we transform this into r squared plus ar plus b equals 0. We solve for r. Depending on r, we write our answer. That's like literally it, right? So if r is r1, r2 real and distinct, so for example, r1 equals 1 and r2 equals 2, then you just plug into this to get your solution for yc. Okay, if r is imaginary, which is potential, right, because we're solving a quadratic, if we have imaginary roots, then we plug into this form right here. And this, you can derive all of these just by doing out some algebra, but it's not necessary to spend time on right now in terms of like knowing how to actually solve these. Okay, the last case is where, okay, r1 and r2 are real, but they're repeated. So for example, if I solve r squared plus ar plus b and I get r equals 2 and r equals 2, as in this would factor into like r minus 2 squared equals 0, and then I would get two solutions for r. Okay, in this case, you may say, okay, I'm just going to go and do what I have up here. I'm going to say yc equals c1 e to the r1t plus c2 e to the r2t, and r1 and r2 are just 2. But notice how these two can all be combined into maybe like I can add the constants and turn that into c3 e to the 2t. And that's not good because a second order ODE will always have two solutions. Okay, it will always have two linearly independent solutions. Notice how these two solutions are not linearly independent. That's bad. So what do we do? To make the second solution linearly independent, we multiply by a small little t before anywhere. Like we just multiply it by a t. Okay, this works. You can test it. But it's also just, you can just know it and know how to do it. You multiply by a t, right? It allows us to ensure that our solutions are linearly independent. Now, I can't add them and combine them together. Now I have one linearly independent solution here and the other one right here. Okay, if I had a third term, right? I would if I had a third, I would do C3 multiplied by t again to get t squared and then e to the 3t. So continuously multiply by t until your solution is linearly independent. Okay? Let's do an example down here. Any questions about the actual process? Because now it's going to be a few examples. Y double prime plus 2y prime plus 2y equals 0. Rewrite it as a quadratic equation. So r squared plus 2r plus 2 equals 0. Solve for r. We get imaginary roots where a equals -1 and b equals 1. And plug right into here, and that's your answer. Simple. Okay. Now, this is a general solution with C1s and C2s. As you may have seen with differential equations before, is that we can have initial condition problems where then now they're going to want you to solve for C1 and C2 given some initial condition. So let's look at the same problem above. Now y0 equals 3 and y prime of 0 equals 1. Unfortunately, there's no way to go about this other than doing the algebra. So, right, we know our solution is this. So y of 0 being 3 means if you plug in 0 for t, right, e to the -0 becomes 1, cosine of 0 becomes 1, so we get c1 equals 3, right? Something like you go through like that, and you can solve for c1 and c2. Right, I think that gives us c1, and then to solve for c2, we need to use the second one, which is that y prime of 0 equals 1. So to take the derivative of this, which is a bit annoying, a bit messy, but at the end of the day, this placement test may have a lot of arithmetic on it, so just be prepared for that. And then you solve for c1 and c2. It's just a system of equations. Okay. And then you can say, okay, the particular solution. So there's a little bit throwing off. This is not actually yp from before. This is this is the like solution with initial conditions, but this is still yc, the general solution for the homogeneous equation. Okay. For some reason here we're missing the non-homogeneous part for this. Okay, which is a little bit. Did I skip it somewhere? Okay, here there's a section of here that's not in the notes. We'll add it afterwards. But okay, so I'll just do it. I'll do it on the side here. Okay, so we've figured out how to solve y double prime plus ay prime plus by equals 0. Now, how do we solve? So this we know how to do. How do we solve y double prime plus ay prime plus by equals f of, let's say y is a function of x for now, f of x. We did t before, so let's do t. F of t, right? Where now it's not 0 on the right side, but it's something here. Okay? Basically, depending on f of t, okay, first of all, remember, when we're solving any differential equation, we have to split this up into steps, right? First, we find yc, so that's going to be simple. We know how to do that, check, right? Then we find yp. Okay, so yp, how do we actually solve for y double prime plus ay prime plus by equals f of t? Depending on f of t, we just take an intelligent guess. Okay, so let me pull up, give me a sec. Let me pull up the table because it should be in the notes here. Hold on. I think we just used like a little bit outdated like a not updated version of the notes. Okay. We want constant coefficients, and then okay, so the main ones to know are the 4 cases on the right where let me make sure I'm sharing again. Okay. There's 4 cases to know. So the first case is where, depending on f of t, we're going to take a guess. So this is called the method of undetermined coefficients. Okay, what that means is we basically guess an answer for yp, and we plug it in and we see what our coefficients are going to be. So given f of t, this is going to be our guess. So it's like another table to add to your notes. If f of t is of the form something times e to the at, we're going to guess something times e to the at. Okay, if f of t is of the form something times t squared, we're gonna guess a t squared plus bt plus c. And if you have t cubed, you just add more terms. A t cubed plus bt squared plus ct plus d, or whatever. If it's of the form m times sine of at, we're going to guess a times sine of at plus b times cosine of at. If f of t is of the form m times cosine of at, we're going to guess the form a, the same exact form. Okay, and all of these guesses should make intuitive sense. If we're saying, okay, y double prime plus something times y prime plus something times y equals something times e to the at, my y's also have to be of the form e to the at, that they add up together to something times e to the at. With sines and cosines, right? If f of t is sine of t, sine of at here, we can't just guess sine of at. Why? Because if y is sine of at, right, then y prime is going to be cosine of at, and y double prime is going to be negative sine of at. So sure, these two may combine to get our sines, but this cosine of at is never going to disappear. So the way we get it to disappear is to not just guess sine, we guess sine and cosine. So that way in each one of these terms, we're going to have, right? We're going to have a sine of at and a cosine of at here. We're going to have whatever, negative cosine of at, we're going to have a cosine of at and a negative sign. But in each one of these terms, we're going to have cosines and sines, so there's a chance of them canceling out, and they will cancel out. Okay. I also need to pull an example, but basically the steps are, right? You take a guess for yp, and then as from here, then you plug it back into your original equation, okay? And then you solve for whatever these coefficients have to be. Okay, and that's your particular solution. So let's do an entire example. I don't think we'll have one. We might have one at the end. Let's just do that example if we have it. Can't zoom out. Okay. Scroll down. Okay, hopefully. Yeah, like this one. Let's do this one right here. Okay, let's do this quickly. So find a general solution. So here we have a non-homogeneous second order constant coefficient differential equation. So first step is going to be find yc, then we're going to find yp. So yc, let's do that real quick. So yc is going to be, this is going to turn into r squared minus 6r plus 9 equals 0. Remember, yc we're solving. I'll write out the steps one more time. We're solving y double prime minus 6y prime plus 9y equals 0. So we get r squared minus 6r plus 9 equals 0. So r minus 3 squared equals 0. So r equals 3 and r equals 3. Remember, repeated roots mean that our solution for yc is going to take the form c1 e to the r1 times t plus c2 times t e to the r1 times t, r2 times t. So make sure to add that t in there because 3 and 3 are shared. Okay. One more thing I forgot to mention is that, oh, this is a perfect example of it. Okay, this is a perfect example. So now we're solving yp. So now we have y double prime minus 6y prime plus 9y equals 4 e to the 3t. So our f of t is of the form m times e to the 3t. So we're going to guess, right, something times e to the 3t. Now there's an issue, okay? The issue is that our guess is going to be useless. Why is our guess going to be useless? Because look, the guess that we're guessing, e to the 3t, is already contained in the solution, right? We already have a solution for it. We know it's a solution. So it's not going to give us any new information, right? So remember, anytime we're dealing with that issue, what do? We multiply by a t. So we're not going to guess a times e to the 3t. We're going to guess a times t e to the 3t. But then you go, okay, that's another issue. Look, this, right? This is still overlapping with this. Okay, no worries. Let's guess another t, multiply by t again, and get a t squared e to the 3t. Now we have a clean guess for our y. So our guess is that yp equals a t squared times e to the 3t. Okay, let's see how bad this algebra is going to be, and then maybe we can cut it short. But the next thing you're going to do, right, is that you're basically going to take your guess and plug it into here. So to do that, we need to find y prime. So the derivative of this guy is the derivative of the first, so 2at times the second, plus the first, so at squared, times 3e to the 3t. And please put in the chat if I make a algebra mistake, because that's, a very high chance of happening. Yp double prime is going to be, okay, derivative of this guy is derivative of the first, so 2a times the second plus the first times the derivative of the second. Okay, hopefully you get the idea. It's just gonna be, you're gonna take that, you're gonna plug it into here. Bunch of terms are gonna cancel out. All of these e to the 3t's are gonna cancel out, and then you're just gonna be left with you're gonna be left, the at squared should also cancel out eventually, and then you're gonna be left with solving for a, and you should be able to solve for a and get like, okay, a equals whatever, 1/3 or something, and then that becomes your guess. So then you would say, okay, so now you know yp, because you know a is 1/3, it's going to be 1/3 times t squared times e to the 3t. And then your final solution, general solution, is yc plus yp. So that's this guy plus yp. And notice how yc's are always going to have c1s and c2s, but yp will always be a particular solution. It will have an exact constant in front of it. Okay, so your entire solution would be, okay, c1 e to the 3t plus c2 t e to the 3t plus 1/3 t squared e to the 3t. Okay, and this is the perfect example problem for figuring out how that repeated thing works, because like it literally comes up everywhere. It comes up first even when you're just solving the homogeneous scenario, then it comes up again when you're guessing. So good example. Okay, now, so a quick recap. Let me zoom out a little bit. I can, okay. A recap is that we are able to solve first order ODEs, right? Either homogeneous or non-homogeneous using two techniques, separation of variables and integrating factor. Okay. Second order ODEs, right? The key idea is that y general equals y complementary, so the homogeneous solution plus the particular solution. We know how to do this for constant coefficients. Okay, that's where we're at right now. Now we're going to look at a specific case. So in this course, you're not going to learn how to solve any type of second order differential equation. We're going to learn specific types. So the next type that we're going to learn is Cauchy-Euler equations. So before we were dealing with constant coefficient, that's where these coefficients were all constants. But if you notice, now they're not. Notice how the coefficient for every derivative term is not constant anymore. It's a function of x. Okay? Cauchy-Euler equations have the form, okay, the second, when you see a y double prime, the coefficient in front of it should have something x squared. Okay? If you see a y prime, it's like y double prime should have some sort of x squared in front of it. So the coefficient of y double prime should be x squared. Y prime should be x. And y nothing should be 1 or a constant. Okay? So x to the 0. So you're x squared, x to the first, and x to the 0. So basically, that's how you recognize whether it's a Cauchy-Euler equation or not. So this is a Cauchy-Euler. Why? Because we say, okay, y double prime, what's the x term in front of it? X squared. Y prime, x, and y is just a constant. And then here, again, can be homogeneous or non-homogeneous. No worries. F of x is either going to be some like random, maybe m times e to the 2t or something, or it can be 0, and that's the homogeneous case. But the same thing applies. We're still going to do y equals yc plus yp. Okay. So how do we actually solve these? So remember, for constant coefficients, right, our initial guess was y equals e to the rt, right? For Cauchy-Euler, our guess is that y equals x to the p. Okay. Trust me, when you plug in x to the p, if you think about it, right? If you have x to the p here, if y equals x to the p, correct, then y prime is going to be px to the p minus 1, and then y double prime is going to be p squared x to the p minus 2. Correct? Oh wait, px to the p minus 1, and then p squared x to the p minus 2. Yes. Okay. Then notice how like the x squares and the p squares will align, and everything will nicely cancel out. So let's just do an example. Let's do an example. And then based on your P1s and P2s, you're going to put it in the solution form. Same idea. Make this table and just plug into the table. A key thing to note is that notice for the repeated roots case, before we would multiply just by t or just by x, right? Here, to deal with repeated overlapping solutions, we don't multiply by t, we multiply by ln of t or ln of x, so natural log of x. Same thing with guessing. If your guess is a repeat, you're going to multiply by the natural log of t or x or whatever, not by x itself. Okay, let's do an example. Okay, so, and then same thing. So here, okay, here's a nice table. This table should have existed for the homogeneous case, for the constant coefficients case, but I think we forgot to put it on. But here's like a nice table where, okay, if this is your f of x, then here's your guess. Okay, notice how with Cauchy-Euler it's a little bit different, but again, put this on your cheat sheet and guess, and then do the algebra. Okay, let's do an example. So here's a homogeneous case. So we really only have to solve for yc, right? There's no yp to solve for at all. So what we guess, right, is y. Oh yeah, okay, that's why I was making a mistake. It's not p squared. Sorry, if y equals x to the p, y prime equals px to the p minus 1, and then oopsies, well, px to the p minus 1, and then y double prime equals p minus 1 times p times x to the p minus 2. I forgot the power rule for a second. Anyways, okay, so we guess y equals x to the p. So we get y equals this, y prime equals that, and y double prime equals that. Then we plug into the original equation, and notice how things are going to cancel out. So we're going to get x squared times y double prime, right there, minus 3x times y prime plus 3y equals 0. And the x to the p's, right, because you have x squared and x to the p minus 2, that's going to turn into x to the p. So these two are going to combine into x to the p, right? This x and x to the p minus 1 is going to also combine into x to the p, and this x to the p is also just going to be x to the p. So at the end, these x to the p's are going to cancel out, and you're going to be left with something nice, which is that p times p minus 1, you're going to be left with a quadratic in p. And you solve for p same way, same before, and then plug into the table. Okay? Yes, those are Cauchy-Euler equations. Any questions on the differential equation stuff we've done so far? Okay. It's just calculation. Okay. The next thing, this is something new. This is something more specific to Penn's course again. We introduced this idea called the Wronskian. Okay, and there's guaranteed to be a question on this on the placement as well. So make sure you know it. The Wronskian for two functions is defined as this. It's a matrix where you basically it's actually defined as the determinant of the matrix where in the column you put f1 and then the next you put its derivative. F2 and then its derivative. It's best to see with an example. So if your first function is e to the 3t and your second function is e to the t, you form the Wronskian by taking the determinant of a matrix where you put f1, so e to the 3t here, then take its derivative, 3e to the 3t. And then f2 equals e to the t, and take its derivative, e to the t, and then you just take the determinant. So you do this times this minus this times this, so you get e to the 3t times e to the t, it's shown right here, e to the 3t times e to the t, minus e to the t times 3, e to the 3t, blah, blah, blah. You get the Wronskian. And that's how to calculate it, and that's how it's defined. Why does it matter? Because if we find that the Wronskian is equal to 0 for any choice of t, as in if you find me a t where the Wronskian is 0, that means that our functions are linearly dependent. So in the same way, remember, vectors are linearly dependent if you can't. Vectors are linearly dependent if you scale one and you can get the other. It's the same way for functions, right? Like f1 being 5x and f2 being 10x, these are linearly dependent functions because I can take a number, a constant, times f1 and get f2. Okay, but the Wronskian basically allows us to do a test to see if these functions are dependent or not. So if the Wronskian equals 0 for any t, then they're linearly dependent. But if you can test every single t in existence and the Wronskian never equals 0, then the functions are linearly independent. So first, let's take a look at these functions here. These are clearly linearly independent, right? I can't take a constant times 1 and get the other, because 3t here and 1t here. The Wronskian also shows this. The Wronskian comes out to this, and negative 2 e to the 4t will never be equal to 0, no matter what you choose for t, right? That's a property of the exponential function, right? It'll asymptote towards it, but it will never actually get to 0. Okay. That's kind of the introduction to the Wronskian. The more important reason that the Wronskian will come up in problems is this form right here. It's a property of the Wronskian. If your differential equation is a second order and it has this form, okay? So remember, we've solved two types. We've solved where, okay, this is the general form of a second order ODE. We've solved when this guy and this guy were constants. And then we've solved Cauchy-Euler, where this has like an x squared in front of it, this has an x, and this has nothing in front, or a constant, okay? However, the Wronskian will allow us to work with even more general situations where P of t and Q of t don't necessarily have to follow the similar constraints that we were talking about before. Okay, so this is like the key equation. The derivative of the Wronskian is equal to negative P of t times the Wronskian itself. Okay, and you'll see where that'll come in, and it will help us solve very tricky problems. These problems are the most difficult. I would think they're the longest and the most involved. But let's go through an example. Okay, there's two types of problems. So the first type is going to be a problem like this. Find a homogeneous second order ODE that has y1 equals t and y2 equals e to the t as solutions. This is confusing because normally we're given the differential equation and they ask us for the solutions. Here's the opposite. They've given us solutions and and they want us to find the differential equation. Okay? So let's use this fact here. Okay, we're gonna use this equation here. How do we do that? Let's first find the Wronskian. How can we find the Wronskian? We're given f1 and f2, right? We know the solutions are y1 equals t and y2 equals e to the t. So we form the Wronskian, right? y1 is t, y1 prime is 1, y2 is e to the t, and its derivative is also e to the t. Okay, then we take the determinant and we get this expression for the Wronskian. Okay. Now we need to use this second equation. Now that we know what the Wronskian is, we know the Wronskian as a function of t is e to the t times t minus 1, right? We can now plug into here and solve for p of t. That's the idea. Okay. So to do that, we're going to need to find the derivative. So the derivative of this is just going to be a product rule again, right? Derivative of the first times the second plus the first times the derivative of the second. We can do this actually done right here, right? The algebra tells us that this simplifies to t e to the t. Okay, so we have w prime of t and we have w of t. Now we're going to take that and plug into this equation. So what's that going to look like? It's going to look like w prime of t, so t e to the t equals negative p of t times w, e to the t times t minus 1. Okay, so I'm noticing that these guys are immediately canceling. And I think I'll also show the solution obviously underneath, right? The e to the t's cancel, and we immediately are able to solve for p of t right here. So p of t is negative t divided by t minus 1. Okay, we solve for p of t. That's good. Remember, our form, our actual differential equation is going to be of the form y double prime plus p of t times y plus q of t, p of t times y prime plus q of t times y equals 0, right? And now we found p of t. The question is, how do we find q of t? Well, we know what p of t is, and we know we know two solutions for y, so we can plug in p of t, plug in a solution for y, and then do out the algebra to solve for q of t. In the sense that let's take our second solution, for example, we know y equals e to the t is a solution, right? That means we know y prime is going to be e to the t, and y double prime is going to be e to the t. Correct? Then we plug those in. So y double prime is going to be e to the t plus, we know p of t already, we solved it. It's negative t over t minus 1. Right? Y prime is e to the t plus q of t times e to the t, because y is e to the t equals 0. E to the t's cancel, and again, we can solve for q in a similar manner, and we get 1 over t minus 1 for q, I think, as we see here. Okay, and there we go. That's how we've now found p of t, we've now found q of t. We can put it together into the form y double prime plus p of t times y prime plus q of t times y equals 0. Okay, any questions on that problem? That's the first type of problem where you'll want to use the Wronskian. The second type is even longer. I think this, like, yeah, the solution is like 3 pages. So let's walk through it, okay? Here's the problem. The function y of t equals t is one solution. So they give us one solution of the differential equation. And again, this, like, do you see what I mean? This differential equation, like, you don't know how to solve it. No, like, I don't know how to solve this on my own. Like, this course doesn't teach you how to solve something like this. So if they just asked you this, that wouldn't make any sense. But the fact that they already give you a solution is a hint that they want you to use the Wronskian to find the other solutions. The first thing, a big mistake people make, is they don't put it into standard form. Make sure your standard, all this Wronskian stuff will only work if your original equation is in standard form. So we divide by t squared minus 2, and we get this, right? We divide everything up by t squared minus 2, and we can now, we're like going in reverse. Now we can immediately identify p of t and q of t. So just as a logic, like as logical steps, in the previous problem, we were given the two solutions, we found w, we used w to find p, and we used p to find q. And then we plugged in p and q, and that was our answer. Here, we're given p and q, we're going to use p to find w, okay? And then we're going to use w in combination with one of these solutions already to find the other solution, okay? Confusing? Let's walk through the logic. So again, just like that was the overall steps, right? Here, we have p of t, and we're going to use the relationship between w and p of t to solve for w. So again, we know w prime of t equals negative p of t. So negative of this is going to be 2t minus over t squared minus 2 times w of t. Okay, I'm going to remove the of t. So it says w prime equals 2t over t squared minus 2 times w. Now, if you notice, this is a first order differential equation, right? We want to solve for w. This is a first order separable differential equation, right? We can bring all the w's to one side and dw in a sense. But honestly, we can just bring w over to one side. W prime over w equals 2t over t squared minus 2, right? And then we can integrate both sides, correct? And if we integrate both sides, I'm going to write it here. I'm moving over here. So this guy is, oops, it's coming all the way over here. Okay, that's an arrow. The integral to the left, so the integral of w prime over w is just going to be natural log of w, right? Because if you take that derivative, you get 1 over w and then chain rule times w prime on the top. And then the integral of this guy is going to be ln of t squared minus 2. Again, based on the chain rule, right? You take the derivative of this, that should be clear. Right? Now we can solve for w, plus some constant here. And we can solve for w, and we get e to both sides, right? We get we get w equals, and that should actually, let's go down, it should be down here. Wait, w prime over w equals that. Integrate both sides. We get ln of w, blah, blah, blah. Ln of w equals ln of t squared minus 2 plus c. We get w equals e to the that, which is, again, e, the constant comes out, and we just get some constant times t squared minus 2. Okay, and the idea is this constant is kind of unnecessary. We can just choose it to be whatever we want, just to get a clean Wronskian. Okay, so in the steps, you can say now that the Wronskian equals t squared minus 2. That's great. We have the Wronskian, but the Wronskian alone is, right, y1 prime, and then y2 and y2 prime, right? Gives us the Wronskian. However, we do know what y1 or y2 is. We know one of the solutions. We know that y1 equals t is a solution. So you can plug that into the first column. Okay, so y1 equals t is a solution. So here the top left corner is going to be t, and then here is going to be 1, correct? And then we can find the Wronskian, and we know that the Wronskian is going to equal t squared minus 2 at the end. We can find the Wronskian this way and say, okay, t times y2 prime. I'm gonna start removing the of t now. So t times y2 prime minus just y2, right? Minus 1 times y2 equals t squared minus 2. Okay, almost there. Now, again, the goal is to solve for y2, right? We know y1. We want to find y2, so we can find the general solution. And the general solution is going to be some constant times y1 plus some constant times y2. So we really have to figure out what y2 is. So how can we figure out from what y2 from here? This is another first order differential equation, and it doesn't look to be separable, right? I don't think we can split. I don't think we can split cleanly. I think it's going to be an integration factor. Let's see what the notes say. Yeah, it's going to be an integration factor, right? So here's the original what we were looking for, right? Let's turn it into standard form by obviously dividing it by t, and we get this diff eq right here. Okay, and we do the division now, and we get this is our new division, our new differential equation, right? Definitely not separable, and that's fine because we know how to use the integrating factor, right? This is of the form y prime minus p of t times y equals q of t, and we know what p of t is, right? P of t is the number in front of here, equals negative 1 over t. So we do the integrating factor equals e to the integral of p of t dt equals e to the integral of negative 1 over t dt. It's all done here. This becomes negative ln, and then that should become 1 over t inside. So we get that the integrating factor is 1 over t. We multiply both sides by the integrating factor, right? And we get this, okay? I'm sort of going fast over this because this is something you should be able to follow just by reading the notes. And then remember, the whole point of the integrating factor is that the left side can always be written as a product, the derivative of a product. So you do that rewriting as, and then you integrate both sides, whatever, and you solve for y2. Okay, so you solve for y2 as t squared plus 2 plus some constant times t. Okay, and so the solution, right, the general solution, y, is some constant times the first solution plus another constant times the second solution. So in this case, right, we know it's going to be c1 times t, because y1, our first solution was t, plus c2 times t squared plus 2 plus ct, right? And then this can be split up into c1 times t plus c2. You can do a little bit of algebra. c2 times t squared plus c2 times 2, so plus 2 times c2 plus c2 times ct. And I think here in the solution, right, the this and this comes together into like one ct term, and then you're left with your final solution being c1 times t plus c2 times t squared over c2 times t squared plus 2. Yeah. Uh, that's kind of a long problem, but those problems do come up, and there's a good chance that something like this will come up. So it's nice to know like the step-by-step process of how to go through that. It's pretty much the same thing every time. It'll just be with different numbers. Okay, any questions about that? To be honest, if the C stuff was a little bit confusing, you could have also just omitted the C here. And then if it makes it a little bit cleaner. If you just omit a C here and don't think about a C, then you're left with y2 equals t squared plus 2, right? And then you'll get, okay, y1 equals t. Then your overall solution is y equals c1 times t plus c2 times t squared plus 2. Either way. Okay. Here are practice problems for, let's see if there's any good ones. What time is it? It's 5:08. I think let's save these for later. And come back to them. Let's first finish the chapter and the material, and then we can come back to the practice problems. Okay, so the last big chapter is we've done first order. So let's just do a quick recap. Right, we've done two types of differential equations. We've done first order ODEs, right, and then we've done second order. Okay, right, and then second order we've done two types. We've done constant coefficients, right, constant coefficients, and then we've done Cauchy-Euler. right? And Cauchy-Euler, we, again, in general, with specifically second order, in our case, we want that y equals yc plus yp, always, right? So for Cauchy-Euler, to find yc, we guess y equals x to the p, and then do the algebra, solve whatever quadratic in p, and we get our general solution. To solve yp, we guess based on the table, right? Based on what that table said, that's called the method of undetermined coefficients, right? And just be smart with your guesses. Make sure to like multiply, right? Here we multiply by ln of x if there's overlap. Okay, constant coefficients, right? To solve yc, we solve r squared plus ar. So constant coefficients are going to be in the form, Cauchy-Euler of the form something times x squared times y double prime plus something times x times y prime plus something times y equals 0 or equals f of t, right? Constant coefficient looks like y double prime plus a y prime plus by equals something, okay? To solve for yc, we say, okay, r squared plus ar plus b equals 0, and then use the table to get yc. To solve for yp, we say, okay, guess based on, same thing, based on table. And that's the method of undetermined coefficients. And here we multiply by x, just x for overlap. First order, either separable or we use the integration factor. Okay, hopefully this table or whatever this thing is called, this tree, should make it somewhat clear of like the structure of like when you see a problem, you should categorize it as one of 1, 2, 3, or 4 scenarios, and those are going to be the 4 scenarios that require you to do it out by hand. Okay, then again on its own thing is the Wronskian, right? And then we talked about the Wronskian. Make some space. Okay, so the Wronskian is defined as the determinant of. By the way, it was for 2 by 2s as the example, but it can be like we can have a 3 by 3. If we have f1, f2, f3, then it just extends down. So f1 prime, f1 double prime, f1 triple prime, f2 prime, f2 double prime, etc. That's what the Wronskian is defined as the determinant of that matrix. If the Wronskian is not equal to 0, if the Wronskian is not equal to 0 for all t, then they're linearly independent, right? The functions are linearly independent. And then we also know that w prime equals negative p times w if you write your equation as y double prime plus p of t times y prime plus q of t times y equals 0. Okay, a lot of information, but that's like the core you need to know to do well on the placement exam. Okay. Any questions on that before I erase this tape chart? Okay. Lastly, if as if one differential equation wasn't enough, now let's do multiple. So systems of equations, now we have systems of differential equations. And here's an example of one. X1 prime equals 2x1 plus 3x2 and x2 prime. Again, we're using x1s and x2s now because we're like grown up and we don't want to use x and y. This system, just like other systems, can be represented as matrix form in matrix form as below here, right? The matrix multiplication works and same thing. Okay. Common thing in terms of notation is that, which I don't really like that much, but we'll generalize this as x prime equals ax. Okay, where it should be all the time, x's should have vectors all them to show that x is actually a vector, right? X is not just one variable. X is implicitly x1 and x2 all the time. Equals a, which is your matrix, times x times x. So x1 prime here is going to be x1 prime and x2 prime. You take the derivative of each element in your vector. Okay. So always remember that in your head. Like for intuition, you can't like x, this is not like the x you're used to seeing, right? This x is a vector of a bunch of different variables in it. We just encompass it as x. Okay. The main idea is we're trying to solve x prime equals ax. See, I'm going to forget to write the vector, so I'm just not going to write the vectors because otherwise I'll forget sometimes and not forget other time, remember sometimes, but all the time Remember, x is a vector in when we're solving these, okay? So in general, I'm saying the derivative of something equals a equals a multiple, some constant times itself, right? That should lend you to a very nice guess, which is e to the lambda, e to the something t, right? And here's what we do is like let's guess this solution. So if you look right here, we're guessing. Let's guess that x equals e to the lambda t. And remember, we can't just guess like a e to the lambda t. Why? Because a to the lambda t, if a is just a number, sorry, a is a bad example. I can't guess like some constant times e to the lambda t because this is one dimensional. X is a vector. X is a vector of x1 and x2. So we need to, instead of guessing one constant, we have to guess two constants. So we have to guess e to the lambda t times v, where v pretty much looks like constant 1, constant 2, right? So that gives me a correlation between x1 would be c1 times e to the lambda t, and x2 would be c2 times e to the lambda t, okay? So that needs to make sense in your head, why we're multiplying here by a vector v. So v is not just a number, it's a vector of two numbers in this case, okay? So let's guess this solution, and let's plug it in, right? So if x equals e to the lambda t times v, then x prime is going to be lambda e to the lambda t times v, correct? Now let's put this back into the equation. So x prime equals lambda e to the lambda t times v equals a times e to the lambda t times v. And notice how e to the lambda t go away, and we're left with lambda v equals av. In other words, av equals lambda v, and that should like light up, that should make your day, because that's the famous eigenvalue equation that we've seen so many times, right? A vector multiplied by a matrix ends up as a scalar version of that vector. So pretty much, if this is our guess, right, it looks like it works as long as v and lambda are eigenvalues and eigenvectors. So pretty much what we're going to do to solve x prime equals ax is we're going to find eigenvectors and eigenvalues of a, and then we're going to plug back into our guess, right? Like if from here we get that, okay, eigenvalue is 1, eigenvector is 1, 0, then boom, that's the solution to our guess. That's our guess with the coefficients solved. Okay. All right, so that's the intuition on how we're going to solve x prime equals ax. So again, to solve x prime equals ax, find eigenvectors, find eigenvalues, find eigenvectors, and then you form this solution right here. So the general solution is going to be x of t. So x, I'm going to drop the t's everywhere. But remember, x is, again, a vector of, I'll even write it. So x, which is equal to x1 all the way down to xn, is equal to c1 e to the lambda 1 t times v1. And remember, v1 is going to be a vector, plus, so this is v1, plus c2 e to the lambda 2t times v2, just like that. Okay, etc., all the way down to the nth one. Okay. Now, this is like the most probably confusing part of the course, like most annoying part of the course. A as a matrix, there's like three possible scenarios. So if A is a matrix, so you have a matrix A, right? Scenario one, it's diagonalizable. So diagonalizable, check. Scenario two, it's not diagonalizable. Okay, if it's not diagonalizable, then we know we're going into Jordan canonical form. Right? And we know it's not diagonalizable because AM is not equal to GM for all the eigenvalues. If AM does equal to GM, and we're diagonalizable, we have two subcases where we either have real eigenvalues, so lambda 1 through lambda n, all real, or lambda 1 through lambda n could be imaginary as well, complex numbers. Okay, so we need to deal with each of these cases separately. Okay, as you might expect, this case is going to be the easiest. If you see an example of this on your test, you should be very happy. This is just going to be just as easy, but just more algebra, which means it's harder, I guess, because more likely to make a mistake. This one is going to be extremely annoying, but we're going to figure out how to deal with all three. Okay. Any questions on like what we're about to go like hopefully that set the stage well for like what we're trying to do. But basically, the end goal is we're trying to solve x prime equal to ax for three scenarios of A, where either A is diagonalizable with real eigenvalues, A is diagonalizable with imaginary eigenvalues, or A is just not diagonalizable at all and it's Jordan canonical form. It has Jordan canonical form. Okay, step one, real eigenvalues. Let's do an example. It's as simple as literally finding eigenvectors and eigenvalues right here. Eigenvalue lambda equals 2. Here's its eigenvector. Eigenvalue lambda equals 3. Here's its eigenvector. You form the general solution, right? Where x, the general solution for x is, remember, x is our vector again, c1 e to the lambda 1t times v1 plus c2 e to the lambda 2t times v2. And then you plug it in. So again, here, right? C1 e to the 2t times the eigenvector for 2, C2 e to the 3t times eigenvector for 3. All right, and it's also very good to always check, like always intuitively check that like this x is really x1 and x2. So x1 is like the top, like you can think about this splits into like the top parts. That's going to be your x1. And then your x2 is going to be like the bottom parts. Your x2 is going to be these guys. So you can also give your solution like this. At least if you give your solution like this, that's fine, but at least in your head, think about it like this. Okay? That's the first scenario. And by the way, if you have 3x3 vectors, it's not going to be any different. If you have 3x3 matrix, if A is a 3x3, right, it's going to be the same thing. C1 e to the lambda. So it's going to be now x, but it's going to be x1, x2, x3 is going to be c1 e to the lambda 1t times v, where v is going to be three-dimensional, plus c2. So it just extends to as many dimensions as you need. Okay, what if the eigenvalues are complex? Then we take this solution. Again, this cosine plus I sine comes from like Euler's identity, which is the fact that e to the ix equals cosine of x plus I sine of x. Okay, so I like when you're doing e to the, like even when we had like R1, when we were doing R squared plus AR plus B, right? When R would equal A plus BI, we would really just be putting e to the A plus BI times t, and then that would split into e to the AT and then e to the BIT, and then we can use the fact that e to the I times something equals that, and then that's how that table is formed. So it's like, it's just doing algebra. So you don't really need to know in detail where it comes from. It's just a bunch of algebra. But here's the general solution. Okay. Now you may be wondering, oh, wait, what? There's only one eigenvector here. And yes, that's because we take the eigenvector for the positive eigenvalue only. Okay. So let's do an example. Let's solve x prime equals ax for this matrix here. Okay. We first find the eigenvalues, and oh man, they're complex. So a 3 plus minus 4i. So a equals 3 and b equals 4. Okay. Now the question is, that's easy to plug in here. How do we find v? V is the eigenvector for the positive eigenvalue. So when we find this eigenvector, we're not going to use we're going to use lambda equals 3 plus 4i. So we do that, we plug in, it's a little bit of algebra. Let's actually go through the algebra one time. Okay, so we're looking to do, I'm going to do it up here in the corner. So we're looking to do a minus lambda I times v equals 0 for lambda equals 3 plus 4i. Okay, so what's that going to look like? A is going to look like, what does A look like? 3, 4, negative 4, 3, minus lambda I. So I looks like 1, 1, 0, 0, and then we multiply by lambda everywhere. So basically here we're going to get 3 plus 4i, 0, 0, and 3 plus 4i. Okay, so what is a minus lambda I equal to? It's equal to 3 minus 3 minus 4i, so negative 4i. 4 minus 0 is 0. Negative 4 minus 0 is negative 4. And 3 minus that, 3 minus that should also be negative 4i. Did I do some math? Sorry, 4 minus 0 is not 0. 4 minus 0 is 4. Okay, now the thing is, right, now the goal is to find a vector in the kernel. So we're looking for some vector times this equals 0. Now, you could row reduce. You could row reduce, and here it'd be like relatively simple. Like you could maybe switch these two rows at least. So let's flip the rows. So -4 comes to the top, then -4i, and then -4i and 4, right? And then you could divide this row by -1 on the top. Sorry, by -4. So you get 1 and then I. And then you could even divide this row down here by -4 if you wanted. Or, okay, let's divide by -4, sure. So we get I and -1, right? And then you could row reduce, as in say like, okay, I want to make this a 0. So I need to subtract I of this. So you could row reduce like that, okay? At this point, with 2 by 2s, it's sort of like you can logic out a guess in a way. So you want to make this equation true, right? Usually the trick is that one of the numbers will be regular, like a real number, and the other will be imaginary. Okay, so in this case, right, I'll say, okay, 1 and I and -1. So you could also just form the system of equations. So call this C1 and C2. So we're looking for C1 plus C2 times I equals 0, and then C1I minus C2 equals 0. And honestly, this is not even too bad, right? You just say from here, you say, okay, C1I equals C2. So C2 equals C1 times I. And then you get C1 plus C2, oh, C1 plus, and then C2 equals C1I times another I. So C1I squared equals 0. And I squared equals -1. So we get, okay, this is, I guess, redundant. C1 minus C1 equals 0. That doesn't help us solve it, right? I guess the other one would help us solve for C2, and then we could choose any C1 we wanted. But I would just try and like do enough examples to be able to kind of logic it out. So in this case, what I'm seeing is like, okay, if I choose 1 for C2, then what works, if I choose 1 for C1, like I works as a number for C2, right? Because 1 and I will make this equation true. So that's how you could find your eigenvector. Okay. So now we have eigenvector for the positive eigenvalue. So um we have all of our information, right? We have A equals 3, B equals 4, and then V equals 1i. We plug that into here. Okay. Notice how this whole thing is just a constant number. It's a number, it's a thing, times V, which is actually going to be two-dimensional. So that's how we get our two dimensionalities, or like 2 dimensions of X there. Okay, so we plug it into the solution form. Now I think if you're out of time on a test, actually if you're on a test in general, if this comes up on a placement and this is like the 6th problem, or the 7th problem, give this and then move on. Don't do these next steps. Okay. You might lose a point or two, but the amount of algebra for the next steps, as you can see, is like ridiculous. It's like it's just annoying, and it's very easy to make a mistake and get like time sucked. What we want to do is here our real and imaginary parts are kind of together, right? Here's real, here's imaginary, here's real. They're not like cleanly separated. So if we just do some algebra out, so the first step that we do is we multiply this whole thing into the vector. So we do it, so this is a number, so times the top and then times the bottom, right? So times the top gives us this on the top, we multiply 1, and times the bottom gives us that at the bottom, right? E to the 3t. Yeah, I think here there's a mistake here. This should be I squared here. And yeah, here that should be an I squared, right? And that's why the I squared turns into negative, whatever. You multiply into the vector. There might be some algebra mistakes here. You get x1 and you get x2. Then you want to pull the vectors with i's. Okay, so there's definitely algebra mistake here, but that's fine. We can do an example of this later on. But all the steps are, if you follow steps A, B, C, you should get the answer. Multiply into the vector, group vectors with and without I together. So you want to pull your i's to one end and your real numbers to the other end, and then add your constants in at the end. So let's come back to this at the end after we finish. Okay. Actually, do we have time? Okay, we have time. Let's just do that. Let's do an example. Let's do it for this problem. So let's actually do it out properly. So if this is our general solution, okay, let's go from here and see if we can actually do the math out because it is important to know. So I'll do it on the side here. So ignore this. Imagine it. Let's assume that this is wrong. Okay, let's take this guy and let's actually multiply this whole thing inside. So my vector is going to become on the top e to the 3t times cosine of 4t plus I sine of 4t times 1, right? So I'll actually even distribute that. So I'll do e to the 3t times cosine of 4t, right? Plus, I'll remove the thing. So I'll just distribute in e to the 3 times cosine of 4t plus e to the 3t times I times sine, I'm gonna write it like that, e to the 3t I sine of 4t. Okay, then for the bottom one, remember we also have an I in here. So it's going to be e to the 3t cosine of 4t times I. So I'll put the I in between, e to the 3t times I times cosine of 4t plus e to the 3t I squared sine of 4t. Okay, that's that. Notice how I squared becomes -1. So I'm going to replace this I squared, and I'm just going to turn plus e to the 3t into minus e to the 3t times sine of 4t. Then group terms with and without I together. So pretty much, right, I'm going to just, I can take these two and like what I can do is I can rewrite this whole thing as the real terms. So the real terms are going to be e to the 3t cosine of 4t. That's the real term from the top. The real term from the bottom is going to be negative e to the 3t sine of 4t. Okay, plus my imaginary terms. The imaginary terms are going to be from the top one, it's going to be e to the 3ti sine of 4t, and then e to the 3ti cosine of 4t. Okay, and the reason we did that is now we can pull out an I from both of those. Oops. Okay, I'll just wait. Okay, so we just get e to the 3t sine and e to the 3t cosine of 4t, correct? And then we add constants. So it's some constant c1 times the first plus some constant c2 times the second. And then this c2 times I is just going to be a constant at the end. So c2 times I is just going to be another constant. So we allow our constants to be imaginary if they need to be. And then this is your solution, like a cleaner solution. Okay. I think this is going to give you full credit and this is going to get you like a few points off. But again, it's not important to go through the algebra if you get this answer. Move on and then come back to it if you have time. Okay. Last case. Let's see. Let me zoom out a little bit. Okay. Last case is where A is not diagonalizable. So that's where A is not equal to PDP inverse, but it's equal to PJP inverse. Okay. So to do this, we're going to do a little bit of a trick. So let's follow along with the steps here just to understand where this comes from. If x prime equals ax, we're looking to solve x prime equals ax, right? We know that A is not diagonalizable, but A is Jordan canonical formalizable. It can be put into Jordan canonical form. So x prime equals PJP inverse times x. So A can be rewritten with PJP inverse. Okay. Now, for simplicity, let's make this substitution. Let's allow x to be equal to P times y. Okay, you'll see why. If x equals P times y, then y equals P inverse times x, just by multiplying by P inverse on the left. Okay, then we get that x prime equals Pj, right? P inverse times x is just y. So x prime equals Pjy. And if we left multiply by P inverse on both sides, so we do P inverse here. So you guys recognize that this P inverse x is just y, correct? Then we left multiply by P inverse here and by P inverse here. So these cancel. And we're left with P inverse x prime, which is just going to be y prime, right? because y equals P inverse x, so y prime equals P inverse x prime. P inverse x prime, that's y prime, equals jy. Okay, why did we do all this? So pretty much our two main equations that we now have are that x equals py and y, x equals py and y prime equals jy. So the idea is that in order to solve for x, right, we're gonna like split it into two steps. Our first step, we're gonna introduce this y, and we're gonna solve y prime equals jy just using the Jordan canonical form. Then, once we solve for y, all we have to do is multiply by p to get our solution for x. So, right, it says it right here. First, we solve for y using y prime equals jy. Then we just multiply it by p to get x. Okay? So, how do we solve y prime equals jy? This is like the most confusing part, in my opinion. Let's use this color. Let's use this color. Okay, so we want to solve y prime equals jy. Then there's an example underneath, okay? But let's say this depends on what j looks like. So if j is, let's say, 3 by 3, okay? It's a 3 by 3 block with eigenvalue equals, let's say eigenvalue equals lambda itself, okay? What does y look like? So before, for x prime equals ax, our solutions were like c1 e to the lambda t times eigenvector, right? C2 e to the lambda t times eigenvector. Only problem is with Jordan canonical form, we don't clearly know what the eigenvectors are. So actually what the eigenvectors become is they become like this. Let me write it out. So y is going to look like, in the 3 by 3 case, c1 e to the lambda t times 1, 0, 0 plus c2 e to the lambda t times t 1, 0 plus c2 e to the c3 e to the lambda t times 1 t squared over 2 factorial. And you're probably like, what is going on here? You will see where this 1 t squared over 2 factorial, that's the Taylor series expansion for e to the x. You will see where it comes in. I actually don't know if we'll have time to go over it like in the recording, but it's explained in the notes. So that should, if you're curious, you should be able to figure out where that comes from. But basically the idea is you have this vector. And what this vector looks like, it's like a chain that looks like, okay, starts with maybe some zeros at the bottom. It starts with 1 t, then it goes t squared over 2 factorial, t cubed over 3 factorial, etc., etc., etc. Okay? And basically what you're doing is like you're sliding this vector down for each term. So originally, for 3 dimensions, right, we start like this is our frame. And here's our 0 and 0 everywhere else, right? Then that's our first eigenvector. Then for the second one, we take it and we slide it down one. This 1 moves here and this t moves here. So now we get 0, 1 t. Then we slide it down again. So the t squared over 2 factorial comes into here, t moves down to here, and 1 moves down to here. We're just sliding it down every way, for every new eigenvector. Okay? That's the case where you have, like, here's an example for 4 by 4 down here, right? Again, this part is constant, similar to how we did it before when A was diagonalizable. However, the eigenvectors are always given by this general form. And that's kind of the idea of doing y prime equals jy. It's because we're isolating the Jordan part and the eigenvector part, right? The eigenvector part is given by p. We can figure that out later. We're going to do that later by doing p times y. So this is not our answer. This is just an intermediate step to get our answer. Okay, so as you can see, right, 1, 0, 0, 0, it slides down. It slides down again, and it slides down again. Okay, it gets a little bit trickier if you have multiple eigenvalues. So let's say in this 4 by 4 case, we'll just follow the example here. Here's the 4 by 4 case, but now we have 2 eigenvalues in our Jordan form. So our Jordan form looks like a 2 by 2 block with lambda equals lambda 1, and then a 2 by 2 block with lambda equals lambda 2. Okay? In this case, what we have to do is the beginning starts the same. So y equals c1 e to the lambda 1t. So the first two are going to be for lambda 1. Our eigenvector is going to look, okay, perfect, 1, 0, 0, 0. Then the next one, lambda 2t. It's going to slide down one. So it's going to be the 1 is going to slide down and then make space for the t. Okay. Plus, now C3, again, oh, sorry, this should not be lambda 2. This should be lambda 1 again, because we have two lambda 1s. So this should be either lambda 1. Now, we're moving on to lambda equals 2. For lambda equals lambda 2. Because we're starting a new eigenvalue, we need to start a new slot for our eigenvectors. All that means is these two slots, right, 1 and 0 have t and 1 have already been filled. So those will always be 0 for the rest of them. Now we basically start the same process, but in this section here. So we're going to start with a 1 and 0 here. Okay. Now we do C4 e to the lambda 2 times, again, these two slots have been taken before. So for the rest of time, they're going to be taken as 0, 0. This part is where we can slide down one and slide our 1 down and make room for a t coming in here. Okay, and that's how you solve for y. Okay, any questions about solving for y, that process of sliding things down and whatnot? If not, we could go to an example, which is right here. Solve x prime equal ax where a equals this. So we find the first thing you have to be able to do is you need to find Jordan canonical form. So this is also a good review of that, but hopefully we find that this is our P matrix and this is our J matrix. Okay, so we find P and J. But remember, the steps are first, we solve y prime equals jy. Then given y, we solve x equals py. That's it. Okay. So this is like the easy step. This is the more hard step. So as you can see, what does our Jordan block look like here? It's a 2 by 2 Jordan block with eigenvalue equals 2, right? So it's going to be, y is going to be c1 e to the 2t, and it's 2 by 2, so it's going to be two-dimensional. We're going to start with 1, 0, right? And then c2 e to the 2t, shift it down. 1 goes down and t goes here. Okay, and that's our solution for y. Then to do x equals py, you just take each one of these and multiply it by p, right? Think about this. Like to do it simply, what I would do is, so let's take this guy, move it up here. I would actually multiply these into the vectors. So like I would write it as y equals c1 e to the 2t and then 0 plus c2 e to the 2t times t, c2 e to the 2t. Then you can take x equals py. So it's going to be p. So, p is the identity. So in this case, it doesn't change anything because you're going to multiply by the identity. You're going to multiply this guy by the identity and multiply this guy by the identity. But either way, you have to multiply by p to get your x's. X equals py. Okay. Yeah, it doesn't change anything because identity. Okay, any questions on that example? It's quite confusing. So like if it doesn't make sense, then like ask what step is not making sense. Okay. The last thing related to this is finding e to the power of a matrix, which is like a strange concept. There's like some like YouTube videos explaining geometrically what it means. So that's pretty interesting if you want to check those out. Here, we'll just talk about how to do it. So how in the world would we ever think about finding e to the t times a matrix, right? E to the matrix. That doesn't make any sense. Well, we use the fact that we know the Taylor expansion of e to the x is given as this, right? An infinite series. Now, if we're looking to do e to the ta, right, we just take in everywhere we see x and we put in ta. Okay. However, this is impossible. This is not nice to calculate, right? If a is some random matrix, right? A is 2, 4, 3, 2. Then a squared is going to be more calculation. Then a cubed is going to be more calculation. And then these are going to continue. This sequence is not guaranteed to converge, right? Actually, I guess it does. It's guaranteed to converge, but it's hard to compute, right? To make it simpler, we're going to use the fact that a is diagonalizable, right? If a is diagonalizable, then a equals PDP inverse, right? And in the same way, e to the ta is going to equal p times e to the td p inverse. So that's like the power of this diagonalization thing, is like we're isolating. The operation we want to do is e to the ta, But to do e to the ta, all we have to really know is how to do e to the td. We don't need to do it, and then p and p inverse just stay a constant, okay? Now, how do we find e to the td? Well, e to the td, if we plug in, right? The only difference is now instead of A being a regular matrix, this is now a diagonal matrix. And for diagonal matrices, it's easy to compute the powers. If your diagonal matrix is like 2, 3, 0, 0, and you do d squared, you can do the math and verify it, but you genuinely just square each one of the diagonal terms. So d squared is going to be 2 squared, 3 squared, which is going to be 4, 9. So it's given d, okay, easy to find. Why is it disappearing? Easy to find d to the power of n. It's like much simpler. Okay, so that's why, right? Taking these diagonal powers are easy to compute. You can read over this, blah, blah, blah. This is a key result. E to the td equals e to the ta over e to the td equals e to the ta and e to the tb, where, okay, so if d equals a, b, 0, 0, then e to the td equals e to the ta 0, 0, e to the tb. Okay, that's a very fundamental result. It's very important to know. So now we know how to find e to the td. So the goal is we're looking to find e to the ta. We know how to find e to the td, check, right? Using this trick right here. So all we do is, right, we know this fact right here. So we're looking for e to the ta. We know how to find e to the td, and we can find p and p inverse because we know how to diagonalize. So that's how we basically find e to the ta for a matrix that's diagonalizable. So if A is diagonalizable, first case here, we first diagonalize it, and find p and d. Then we find e to the td using this fact. And then e to the ta, you're just going to multiply on the left by p and the right by p inverse. Okay? In the case that A is not diagonalizable, which always comes back and is annoying, right? It's not going to be a D matrix here, it's going to be a J matrix. So we have an extra step here. We have to figure out how do we find e to the tj. This right here should be a J here, not A. E to the tj. Here's what you do. Pretty much, it's like a nice trick. You say that any J matrix, right? There's a Jordan block, can be split up into a diagonal matrix, the sum of a diagonal matrix, and what we call a nilpotent matrix, which basically means zeros along the diagonal and ones along the superdiagonal, right? Nilpotent means that if you have a nilpotent matrix n, okay, you can do n squared to it, n cubed to it. Eventually, one of these guys will be 0. Okay, like in our case, right? If n is 0, 1, 0, 0, the first time you multiply it, you get 0. So n squared is 0, right? And that's nice because that means that in this expansion term, n squared is 0, right? So everything after n squared is also, n cubed is also going to be 0, n to the 4 is also going to be 0. So e to the tn, our nilpotent matrix, is given by this, right? Identity plus t times n. I'm also skipping over this quite a bit. So we found e to the tn, right? However, we want e to the tj. So e to the tj is going to be your so e to the tj, right? If you think about it, is e to the t times this, right? Which is e to the t times this times e to the t times that. So we know how to find e to the tn, right? That's done. So all we have to do is now add e to the td. So we already know how to calculate this. So basically what we've done is we've taken J, we've split it up into two matrices. We know how to do e to the power of this matrix. That's a diagonal matrix. And now we just figured out how to find e to the power tn, which is given by this. And n, right, this e to the tn term is going to look exactly like, for 2 by 2, it's going to look like this, right? For 3 by 3, it's going to look like 1, 0, 0. Then it's going to shift down, right? It's going to be t up here, 1, 0, and then t squared over 2 factorial, t, and then 1. Okay. Yeah, that's what your e to the tn is going to look like. And then all you do is you go in, and we'll see that with the example, you multiply by your e to the td, which is just going to be like based on your eigenvalue, the number that you put there. So for example, right, for a 2 by 2 matrix, if this is your Jordan block, right, your lambda is 4, so e to the 4t in front, and then there's a 2 by 2, so the nilpotent e to the tn is going to look like this, right? So you multiply those out, and that's how you get e to the tj. Okay, so now we know how to find e to the td and e to the tj, and so no matter what case we have for a, if a equals pdp, if a equals pdp inverse, then we're good, because what do? We say, okay, e to the ta equals p e to the td p inverse, and we know how to solve e to the td. And if a equals pj p inverse, then we say, okay, e to the ta equals p e to the tj p inverse, and we know how to do this. Now we're good. So here's like a good side-by-side example. For your clean diagonal matrix, e to the td is very nice, clean and diagonal. For your Jordan matrix, it's not. It has your e to the t, right? If this was if you had different eigenvalues, this would just be like e to the 2t or e to the 3t or whatever. But you can see like the constants in front go like 1t, t squared over 2, and the column shifts down. Okay. Let's, before we wrap up. Okay, we're gonna skip. There's actually, okay, there's quick stuff we have to do in the last 10 minutes. The example here should be straightforward, so you can verify. Let's now talk about, okay, so we solved x prime equals ax, right? We figured out how to solve x prime equals ax. No worries. Now what happens, right? This is like our homogeneous version, as in like, this can be written as x prime minus ax equals 0. No worries. Now how do we solve it if we have some f here, if we have like another term here? So see, homogeneous is x prime equals ax, the solution is xc. Non-homogeneous is x prime equals ax plus f, where f is some constants, okay? There's two options to find f. Whenever we deal with the non-homogeneous, one solution will be using methods of undetermined coefficients, which is where you make a guess. The other is this formula called variation of parameters, okay? Let's do the first method first. So method of undetermined coefficients, what do? Solve, here's our example. Solve x prime equals ax plus f, where a equals this and f equals this. So we're looking to solve x prime equals a, so 3, 1, so that's actually write the whole equation out. Oh, I wrote it down here. x1, x2 prime equals a times x1, x2 plus this f. Now remember, the first thing we have to always solve, if we have a non-homogeneous, we always solve that the general solution equals the homogeneous solution plus the particular solution. So the homogeneous solution is going to say, okay, I'm going to imagine you're not here. And this is my favorite, x prime equals ax problem. I know how to do this. I diagonalize a, I find eigenvalue 4 with this eigenvector, eigenvalue 2 with this eigenvector, and I plug into the general solution formula. Done. That's xc done. Okay, now how do we find xp? We take a guess. So what would our guess be? We're given e to the t's, so we're going to guess e to the t. Normally before we guessed e to the t times some constant a, right? But now we need to guess two constants. So we need to guess a vector in a sense. So we need to guess c1 and c2 in one, because we're dealing with vectors here. It's a system of two equations. So we guess that our solution xp is e to the t times c1 and c2 as a vector, okay? In that case, if x particular is e to the t times c1, c2, then x prime is going to also be e to the t times c1, c2, right? Because this is a constant times e to the t. And then we plug in here. So we plug that into what we have here. So x prime equals ax plus f. So x prime is e to the t times c1, c2 equals a times x, right? Which is e to the t times c1 times 2 plus f. And remember, our f was right here. We can factor out an e to the t and be left with 3, 6. Notice how the whole point of us guessing was so that these nice e to the t's will cancel out. And then here's a system of equations. Simple to solve for c1 and c2. Hopefully at this point that should be familiar. We solve and we get c1 equals 0 and c2 equals -3. And so our final solution is, here was our general solution, xc, that we had done at the beginning. And then remember, our guess was e to the t times c1, c2 for yp. And so now we can plug that in and say c1 is 0 and c2 is -3. And so that's our particular solution. So that's x. That one was xc. This is xp, and you add them up, and you get the general solution. This is like the same idea when we were doing it for non-systems, right? Same process. Okay. Now, the last thing in the last few minutes, honestly, this part, variation of parameters, is not likely to come up, but I would put the formula on your sheet. Let's skip variation of parameters. I think it's fairly well explained in the notes. So read over the notes and then follow the example. It's more arithmetic based. I mean, it looks very confusing, but it like the notes will explain it. Okay. The last thing to talk about is okay. I want to be able to everything we were doing before has been solving differential equations, solving ODEs. Now let's do something a little bit easier. Let's take a higher order ODE, so like here a second order ODE, okay, and write it as two first order differential equations as a system. So the idea is that an nth order ODE can be rewritten as a system of n first order differential equations. Okay, so right here, right, let's do this one. So we have y double prime plus 17y prime plus 3y equals e to the x. Here's the steps you do. Okay, we need to figure out, okay, first of all, how many variables are we going to need? Second order, we're going to need two variables. Let's call our new variables x1 and x2. x1, okay, we set equal to y, our first order, and then x2, we set equal to y prime. Okay, and the reason we'll do this, it's like a method. You'll see why this works, okay? Then, again, we're looking to rewrite it as like, these are our two variables, x1 and x2. We want to write it as x prime equals ax, right? Which remember is x1 prime, x2 prime equals a times x1, x2. And a is a matrix, right? So we want to find x1 prime and x2 prime. So if x1 equals y, then x1 prime is going to equal y prime. And if x2 equals y prime, then x2 prime is going to equal y double prime. Okay, but notice how x1 prime equals y1 prime equals y prime, and x2 equals y prime. So we take y prime and replace it with x2. Okay, and the thing is, okay, x2 prime equals y double prime. How am I going to ever know what y double prime is in terms of x1 and x2? Well, look, given this original equation, if we go up here and write y double prime equals negative 17y prime minus 3y plus e to the x, notice how negative 17y prime, that's negative 17x2, right? Because y prime is equal to x2, minus 3y, y is equal to x1, so minus 3x1 plus e to the x. That's just a constant term. We'll deal with that later. So x2 prime equals negative 17x2 minus 3x1 plus e to the x. And notice how, ignore the e to the x for now. We'll just add that on as a vector later. Notice how this is a system of equations, right? We're saying x1 prime equals x2. So x1 prime equals 0x1 plus 1x2. Okay. And then x2 prime equals negative 3x1 minus 17x2 plus some e to the x. So first, let's rewrite this as a system. That's going to be x1, x2 prime equals a. What's a going to be? 0, 1, negative 3, negative 17 times x1, x2, right? And the way we're going to get this plus e to the x at the end is going to just add a vector of 0 and e to the x. I don't know if that's visible or not, but we add a vector at the end that's plus 0 and e to the x. So it won't apply to the x1 prime, but it'll apply to the x2 prime. Okay, let's do a quick example before we run out of time. Another example, a harder example. Okay, blah, 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 blah. Okay, here, let's do this one. Okay, here, this is 5. This one is more tricky to like kind of understand, but let's go through the steps. So for x1, we're going to need 3, and for y, we're going to need 1 more. Okay, so we're going to need 4 in total, right? X triple prime, so x triple prime equals x plus y. X1 is given as x, x2 is going to be x prime, and x3 is going to be x double prime. I think actually we are missing one, so this is not a good example. This example might be incorrect. Let's do wait, let me quickly find. Yeah, okay. Let's do that. Let's do this example right here. Um Actually, let me find a better example. Mm, okay, give me a sec. Real quick. Okay. Systems of differential equations. Oh, not here. Okay, let's do this one. We're given x double prime equals x plus y and y double prime equals 2x minus 3y. So x double prime equals x plus y. And then what was the other one? Y double prime equals 2x minus 3y. Okay. This is the last example, and then I'm also happy to stay like a little bit longer for questions if there are. But if you have to go, then please head out because it's 6 p.m. Also, you're free to go whenever. Okay, so the way we're gonna do this is we're gonna look at we're gonna need four variables here because two second order differential equations. Um, let's let let's do the x's. So we handle this equation up here first. So okay, x1 is going to equal to x, and then x2 is going to equal to, sorry, x1 is going to equal to x, and x2 is going to equal to uh, x prime, okay? And then we say x3 is equal to y, and then x4 is going to equal to y prime, okay? That's our basic setup, right? We're saying of these four variables, the first two, x1 and x2, are going to be from this equation up here, and x3 and x4 are going to come from the second equation up here, right? Now that we have our four, we're again looking to do x1, x2, x3, x4 prime, 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 prime equals something times x1, x2, x3, x4. So we need to find what x1 through x4 prime are. So we need to find x1 prime, which is equal to x prime. x2 prime is going to equal to x double prime. Here, x3 prime is going to equal to y prime. And here, x4 prime is going to equal to y double prime. Now we make some substitutions, right? We know x prime is exactly equal to x2. So this guy's going to equal to x2. So let me do it in a different color. So this is going to equal to x2. Okay. X double prime, not in here, but x double prime is right here. It's equal to x plus y. And x is x1, right? And y is x3, right? The reason why I'm replacing x and y with these is because we're turning it, we're like transforming it into new variables that we define. So everything needs to be in terms of x1 and x2 and x3 and x4. Okay, same idea. Y prime right here is x4. That's nice. Okay, y double prime is 2 times x minus 3 times y. So 2 times x is 2x1 minus 3 times y is 3x3. Okay, now we have our whole system. Now let's plug it in. So we want, let's write this a little bit clearer. Let's figure out what the matrix has to be now, and then we're done. Actually, this is technically, like we already technically did it. Let's write a little bit neater. We already did it when we said x1 prime equals x2, x2 prime equals x1 plus x3, x3 prime equals x4, and then x4 prime equals 2x1 minus 3x3. Right? That's already kind of done, but let's turn into matrix form just to be satisfied. So it's going to be x1, x2, x3, x4 prime equals our matrix. Okay, we want x1 prime to just equal x2, so it's going to be 0, 1, 0, 0, right? The reason I'm getting that, the way I'm getting that is because I'm thinking on the right here, I have my x1, x2, x3, x4, correct? Because we're writing it as x prime equals ax. And I know that when I do this dot product, right, the only way for me to just get out x2 is for me to control that and put a 1 on x2 slot and 0 everywhere else. So for x1 and x2, I'm going to put a 1 here, and 0 everywhere else. x3, I just want x4. And then for x4 prime, I want 2 times x1, 0 x2s, negative 3 x3s, and then 0 x4s. Okay. That's the end of the material. Technically. I know it's a little bit fast at the end. So if you have questions, I mean, maybe we can like pause the recording, like stop the record, or you can even leave the recording. If you have questions, I'm happy to stay on and answer for a bit. So about like anything about like it can be this session, last session, about anything related to the course. Um, I think it would be nice to like go do host something, some sort of office hours thing where we can go over like a past final. And also soon we'll push out like more practice problems because one, half of the practice problems here have mistakes in them, and two, like there are more like genres of problems that you should be familiar with before taking the placement. Um, but yeah, so that will come. In general, is like if there was to be an office hours, would this time like Sunday afternoon, evening-ish work? Like if you just put in the chat, like put in the chat if it doesn't work. And then we can think of another time. But like this course is like you really just need to know how to solve the problems. And even if you conceptually understand the material, which like I tried to emphasize going through this, at the end of the day, you need to just know how to like plug and chug. And speaking of plug and chug, there's a good resource I would recommend. If you go to, I'll write it here. You look up, go to Ivan Ivan Lee's website. Okay. He's a Penn, I think he did his undergrad at Penn. He was a 2400 tutor or like TA. And he made a bunch of videos going over solving example problems. His series is called the Plug and Chug. So his has no intuition at all. He doesn't care about where things come from. He's just like, here's how we solve these problems. So I think that in combination with what's on these notes will make you very prepared for the exam. So yeah. Um, any final questions? Any questions about anything? Stuff to go over? Okay. In that case, I guess we're all good for today. Um, keep an eye out on Canvas for like the office hours schedule, and also keep an eye out for when the practice problems are published. Because hopefully there'll be a lot of them, and the solutions will also be pretty like nicely written, so you should be able to just go through and like grind a bunch of practice problems. Okay,
All right.
thanks, guys.
Thank you, Adam. Thank you
Yeah, yeah.
for everyone who came. Feel free to leave. Um, thank you for going on for the whole entire 3 hours, Adam.
That was long. That was long. This session, like, there's so much material. All right, bye guys. Yeah. Also, if you have any questions before the placement about stuff, just email me. I'll try and get back as soon as possible. But yeah,
All right.
stop sharing.
I
Okay.
don't know. I don't know where Johnny Beck went, but
He's probably like asleep.
So
Oh, he's here.
no, I'm here. I'm here.
I would I
There was
wouldn't I wouldn't blame you if you were asleep. That was
uh,
like,
there was like four people here, bro. Right?
yeah, I know. I mean, I don't know. I feel like I don't see why more people would want to do 2400. Like I can see why a majority. How many were in 1410 in the afternoon?
Like 25, maybe.
Oh, really?
yeah,
Yeah,
yeah, 20,
yeah,
30-ish.
yeah. I mean,
What?
1400 has more. 1400 has like 70.
Okay. Was 1410 also 25 last week?
Yeah, like 30s, maybe
Okay,
35.
okay, 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 okay.
It's not
Wait,
really that
last week there was 12 here, right? 12 or 13?
Yeah, there was a lot more.
8.
I'm
Yeah.
assuming most people are like, I could watch the
The
Watch
recording.
the
video, yeah.
recording.
But
Yeah.
Christina just texted me saying that people aren't watching the videos, so
They're
Oh,
they
they're
they're not?
they're not. Yeah,
Oh shoot. Maybe it's
oh,
not.
yeah. I don't know.
that's
We'll
crazy.
see. Maybe they'll lock in August.
Yeah, I think yeah. I think
I mean, I would
maybe
Well,
watch the
they're
videos
gonna
too
hear
times
this
two.
video when we want, because it's still recording.
yeah. We're calling you guys out. Anyone who's studying last minute, you're getting called
Yeah.
out. Yeah.
Did you
Okay.
announce the office hours, Adam?
I think we can, right? Wait, let me just make sure.
Yeah, I
I,
mean, whatever time you want to do, we can just like make it a Canvas announcement. It's
yeah,
not
yeah.
super.
Let me just
Yeah.
make
I
sure.
mean, it's isn't 1610 is happening Sunday from 3 to 6, right?
Yeah, yeah. I mean,
But I'm
I
guessing
think
one
it's
of us
up.
doesn't have to be here.
I don't think any of us have to. I think Adam's fine on his own.
Yeah, I
Yeah,
think
I can just host it. As long
Yeah.
as like yeah. Yeah, it should be chill. But I also want
If you want.
practice
Sorry.
problems by then. Yeah. So I think let's just do next Sunday, 3 to 6 p.m.
Sounds good. Yeah. I'll like message you later
Okay, sounds good.
to confirm. All right. See you guys. Thank
Sounds
you.
good. Okay.
Okay.
Bye.
Bye-bye.
See ya.